the blackboard if needed, the text on blackboard. Okay.
Yes.
Okay, that's good. I can start then. Well, so I proceed with examples of three important classes of one-Lifshitz maps, automata maps. So we consider now the ring of formal power series. This is like this. You know what are these? And we where C all these C are periodic integers, and we consider mappings defined by them. So we demand that this series converges everywhere on ZP, everywhere on ZP. So in other words, this means that the periodic limit of C is zero. So it tends to zero as I goes to infinity. The class of functions defined by this convergent series is called, we will just denote by letter C, it will be called C functions, and by the very definitions, the C functions are analytic on ZP, so there are infinitely many times differentiable, and moreover, the class is this class is closed with respect to derivations. It's quite clear. You can take the derivative of each function and you obtain the function of that form. And Taylor coefficients are like this. So this is the derivative. That's very usual things. And the most common examples of C functions are polynomials with periodic integer coefficients. Also, this is a C function, and this, for example, is a C function. Well, that's some more. Well, in the nearest future, I need falling factorial powers. Falling factorial powers is like that. So this is defined. This is how define the falling factorial powers. This is a definition. There are combinatorial relations which relate falling factorial powers and ordinary powers. These are still linked numbers, respectively of the first and of the second kind. I just recall that this one is the number of different permutations of n elements that consists of cycles, and this is a number of partitions of n elements in an empty subsets. This is well-known things. Just relation. The next class is called a B function. B function is functions which can be represented everywhere on ZP by falling factorial power series. So these are functions of that kind, where B here is periodic integers, and in other words, f is a B function if and only if we can represent it like this, where these A are periodic integers, but what is important, these are also periodic integers. These are also periodic integers. So you see that these are just Muller series of special form, and because of this condition that all these are periodic integers, and we know by this formula, from that formula, that the order of P of I factorial is that we immediately conclude that all these functions satisfying B functions satisfying these conditions, they are one-Lifshitz functions. Why? By that criterion which we proved yesterday. By that criterion, they are all one-Lifshitz functions. Okay. All C functions are B functions. So this is well, quite clear, short proof. We can express ordinary powers with factorial powers. We get like this. We get like this. And so we just change the summation, and we, as all ck goes to 0, sk periodically, sk goes to infinity, we see that the rightmost series converges, and that's why we have this series is well defined everywhere on ZP. So this is indeed so, but not vice versa. For example, this function, just the sum of all falling factorial powers, or like this, is a B function, just by our definition, but it is not even an analytic function, since this function does not satisfy the criterion. I recall this criterion, the criterion of analyticity, right? It's not so. It's not so. You see, because the coefficients are like that. So, but it is a B function. Now, B functions, they constitute a very good space. Actually, it is a complete metric space. We define the distance between two functions like that. So actually, this is the distance defined by a standard periodic sup normal. It's actually sup norm with respect to periodic distance. Well, I have questions. Oh, sorry, it's not for me. Okay, and this is the norm. Actually, what does this mean? What does this mean? So, in simple words, the distance between two functions f and g is p to the minus n, whenever n is the largest natural integer, so that these functions are congruent one to another modulo pn. This is the meaning. This is the meaning of this distance. And with respect to this distance, the class B is a complete metric space. The class B is closed with respect to additions, multiplications, derivations, and composition of functions. Polynomials with non-negative rational integer coefficients constitute a dense subset here with respect to this norm. The proof of this, I will not give the proof of this theorem, since it is, well, it's purely periodic, but it is a little bit involved. And I need more time for other things. But I just want to mention that though the theorem looks like an analog of Stone-Weierstrass theorem, it is not the periodic Stone-Weierstrass theorem. Since the latter theorem states condition when a uniform closure of a class of functions defined on a compact set, and ZP is a compact set, is a class of all continuous functions on the set. The class B is not the class of all continuous functions on periodic integers. The periodic Kaplansky theorem, there is another theorem which is looking like that, but it yields that all continuous function on a compact set can be uniformly approximated by polynomials over QP. But again, this theorem deals with uniform closure of polynomials over that. And all functions of the closure turn out to be uniformly differentiable, not only continuous. So this theorem cannot be derived neither from Stone-Weierstrass theorem nor from the periodic Kaplansky theorem. These are the theorem of a very important class of one Lipschitz, thus of automata functions, and we proceed with study of this function. This is why it is important. Well, this is a proposition which well, gives us examples of functions from the class B. Let's take two one Lipschitz functions, arbitrary, such that this function is congruent to one modulo p everywhere for all everywhere on ZP. Then this function is well defined well, this is just an exercise. I will not prove this now, but people who want to see the proof can look into my textbook. So this function, and it is a one Lipschitz functions. But what is interesting, if these two functions, these and these are B functions, then this function, the exponential, this exponential function of exponential sort is also a B function. So a very large class of very good functions, well, lies here, are B function. Well, in particular, rational functions, such that the denominator is not zero modulo p, well, arbitrary. So this is this should be, of course, well, Vx, not G. Okay, so Vx over Ux. So this is a B functions if and only if the denominator is not zero. Well, it's also a B function, and the more properties of B functions are that they are locally analytic of order 1. In periodic analysis, there are well, all locally analytic. There is a notion of local analyticity of a certain order. Actually, I will need only of the order 1. The local analyticity of order k means that this development into Taylor series holds when k, well, k and larger k. So the local analyticity of order 1 means that this is true. This is true when k is 1, 2, 3, etc., but not 0. Of course, k must not be 0. And all these terms of all these are periodic integers. This is also, well, a little bit involved proof, and I omit it because actually I only want to demonstrate examples of automatic, means one Lipschitz functions, and this is that this constitutes a very large class of very good functions, and the next, the third class of special one Lipschitz functions, which called A functions, A, B, C, right? And this function is said to be an A functions if and only if it is one Lipschitz, and if there is n, given f, there is n, such that p to the power n multiplied by f becomes a B function. Well, this is well, also a Taylor theorem holds for A functions. It also can be developed into Taylor series, but now this is still a periodic integer, but this may be not periodic integers for general A functions. This is why this class is important, because integer-valued polynomials of a QP, which satisfies Lipschitz conditions with a constant 1, are A functions. This is why we need. Integer-valued means that the polynomials have coefficients from QP, but in integer points here and points from here, they assume values from here, so they map periodic integers to periodic integers. This means integer valued. So, well, the functions of this form, well, polynomials of this form, are A functions generally, and of course any one Lipschitz function on that P can be uniformly approximated by this function. And all the inclusions are strict. For example, this function is an A function, which is not a B function, and these are classes of which we will deal with later. And now I will switch to the one of the main topics of my mini course, the ergodic theory for p-adic von Lipschitz functions. Fortunately, you already know what is Haar measure on this metric space. We will assume that always that Haar measure is always normalized, so that the measure of the whole space is 1. So the Haar measure on this space is a natural probability measure. So this is how now we have a probability space. So this is a probability space, and balls are elementary measurable sets, and the measure of the ball is equal to its radius. Is equal to its radius. Then it's a good measure. I skip all this because you already know this. Now I will need some. I recall some notion of the theory of dynamical system. So we have a measure space with measure mu. S is measure space is measure mu, and F is a mapping. Is a transformation of S, and it is a measurable transformation, which means that every pre-image is of a measurable set is also measurable. Then this is a standard definition of a trajectory or an orbit. This is the same. We just take a point, start iterate it, and thus obtain a trajectory or an orbit. These are the same. This is the initial point, and now we will define another thing. We can apply to the trajectory some mapping F from this measure set to another measure set, also measurable sets, also a measurable map, and this is sometimes it's called an observable. In computer science, it's called an output. This is a terminology. Now I recall that again, for those who knows the dynamical system theory, this is standard definition. If we have the mapping from a measure space to another measure space with measures respectively mu and nu, then it is measure preserving. The mapping is measure preserving if and only if the measure of a pre-image, the values of image and of pre-image are the same. So we take any measurable subset from here, take a pre-image here, and the measure here, this measure and this measure must be the same. This means measure preservation. Now, the next important notion which I will use is ergodicity. The ergodicity is defined for the case when we have two these measure spaces coincide and measures also the same. So a measure preserving map is a transformation of a measure space, and it's said to be ergodic if it is measure preserving. This is I stress it must be measure preserving by definition, and if we have an invariant subset, right? This means that the subset S is measurable and invariant. Then its measure is either 0 or 1. I recall that measure is assumed to be a probability measure. So what in simple words, what means ergodicity? Ergodicity means that measurable transformation invariant subsets of ergodic measurable transformation are either nothing or everything. So it leaves no subset with non-trivial measure, so to say, on its place. It moves everything. Is this clear? Because this is the most important. But maybe you know all this. But if not, then I recall this, and you must understand now what does this mean. Because now I will restate. I'm going to restate this notion for one Lipschitz maps. Is this clear? Yes. No questions about this.
Other questions?
I have a question.
Yeah, no questions.
I have a question.
Yeah.
Just a second. About the definition of measure preserving.
The definition of measure preserving is here. So the measure of pre-image is the same as the measure of image. They have the same values. These both are probability measures.
Is it the same if we set measure of S equal to measure of F evaluated at X at S? Do you know why? Do you know why they consider the inverse image of S instead of defining measure preserving as me evaluated at S equal to V evaluated at F or X? F of X.
So why here is -1, right? This is your question. This is your question. Why in the definition we use -1 rather than simply F?
No, rather than simply S. S there and F evaluated at S in the space Y.
S is in the space Y. The measure of S in the space Y, so the probability to hit the S in Y is this. Now we take a full pre-image of this S here. So this is a subset. This is a subset here, and here it is its own probability measure mu. But the value, because the probability is the number from between 0 and 1. The value is the same. The probability of hitting the set S here and probability hitting its pre-image here is the same. Probability hasn't changed.
Okay.
Is this clear? This is standard definition. It's not mine.
Okay. Okay.
Yeah.
Thank you.
Okay. So ergodicity in simple words means that no invariant subsets which has measure either 0 or no. For example, yeah. This is a trivial but important example. Let's S be a finite set consisting of n elements. It is endowed with a uniform probability measure. So, well, just the measure of subset is the number of its elements divided by n. So, this is the measure, right? The transformation is measure preserving if and only if it is bijective. So, if and only if it is a permutation. Is this clear? And the map is ergodic if and only if this permutation consists of a single cycle. Is this clear? This is standard probability measure on a finite space.
Yes.
Okay.
Yes.
Yes. This should be absolutely clear because I will show that these two things in periodic case for one Lipschitz maps are tightly related. Now I recall another notion which deals with topological transitivity. This is a tricky notion somewhat. So if we have a topological space and a continuous mapping then it is called topologically transitive if there exists a dense orbit, if there exists some x such that the set of iterations is everywhere dense set in this. So means that there is a point in the topological space whose orbit visits any neighborhood of any other point infinitely often. This is dense orbit, and the system is called minimal if every orbit is dense. Every orbit is dense, but the problem is that there are two different non-equivalent of topological transitivity. The second one is here. The map is called topologically transitive if for every pair of non-empty open sets there exists a non-negative integer L such that we move this set such that the intersection is not empty. But luckily, for the case when our periodic for the space of periodic integers and dimensional space of periodic integers, the two definitions are equivalent. They are the same. So the topological transitivity means the existence of dense orbit or this one. So this is good for us. So we shouldn't bother about what topological transitivity we use. The next definition, so it's the standard definition, a mapping is called uniquely ergodic if there exists a unique F invariant probability measure such that F is ergodic with respect to mu. A unique measure. So let's say if we have a mapping F, then there is the only one probability measure with respect to which F is ergodic. And the following theorem, it's a theorem from the theory of dynamical system. A minimal isometry of a compact space is uniquely ergodic. What does this mean? Because we will deal with this class, actually, we will see that measure preserving one Lipschitz maps are minimal isometries. And of course they are on a compact space. This means minimal, that every orbit is dense. This means topological transitivity, and this is what we will we deal with. Now I will. Why we need all this? Actually, we will need this to define uniform distribution of sequences. This is a standard definition of uniformly distributed sequences from the theory of uniformly distributed sequences. Each just the limit of occurrences of some Borel subset or measurable subset makes no difference here. That it is asymptotically must be equal to the measure of this set, and this sequence will be called uniformly distributed, and the sequence of periodic integers with respect to our measure on ZP according to this definition is we like this, that the probability of every modulo pk, if you take this sequence modulo pk, then the probability of then the frequency of any element of from this sequence modulo pk is asymptotically equal 1 to pk. This is just definition. Or for m-dimensional case, this is like this. These are standard notions from the theory of uniformly distributed sequences, and this is the theorem, which is called follows from individual ergodic theorem, which means that this sequence is if the mapping is ergodic, then almost any orbit is uniformly distributed. This theorem has a number of applications, and the most application, this is actually individual ergodic theorem, which well, a very general theorem is like that, and by using this theorem, you can, for example, estimate integrals. So this theorem is used in a number of applied programs, for example, quasi-Monte Carlo, etc. And well, ergodic maps are mostly they are usually working better than just random maps. So I recall this again, this the mapping, this cutting of tails of the mapping model pk, and now I can I will call the if we have one Lipschitz map. One Lipschitz map are good maps because they are the functions, these functions, taking them, reducing them modulo pk for every k, results in a well-defined function on the residue ring. It's a well-defined map, and this map is called an induced function. For Cartesian powers, it is the same. Well, this is the reduced map modulo pk, so we reduced modulo pk every coordinate, and now we can more definitions. One Lipschitz map is said to be balanced modulo pk, or respectively bijective or transitive modulo pk, whenever every induced function is balanced, or respectively bijective and transitive. Bijective, you know what is this? Transitive, you know what is this? What is balanced? Balanced is if a map of a finite set onto finite set is called balanced if the number of elements in every pre-image here does not depend on the point. So all pre-images have the same number of points. Is this clear? This definition?
For example, bijective maps.
This is not bijective because A and B may have different cardinality.
No, but they are an example.
Yeah, yes, for A equal to B, this is just bijectivity. But if B is smaller, the number of elements in B is smaller than the number of elements in A, then it is not the bijectivity. This is just balance. The number of preimages of every point from here have the same number of preimages here. Is this clear? This one?
Yes.
No? Yes, okay.
Yes.
Okay, so we continue. In other words, if we have a transitive mapping, a transitive one Lipschitz map, one Lipschitz map, this one, I'll say one Lipschitz map is transitive modulo pk. This means that this sequence is strictly uniformly distributed. What means strictly? It is periodic, strictly periodic. Its period is p to the nk, so the number of elements here, and each element from these residue rings occurs at the period exactly once. This means strict periodicity. And this is the main ergodic theorem. If M is for one Lipschitz maps, for M equal to n, one Lipschitz function, so M is equal to n, is measure preserving or accordingly ergodic if and only if it is bijective or accordingly transitive, modulo pk for all k. And if n greater or equal to m, then the function is measure preserving if and only if it is balanced modulo pk for all k. So what is this gives a complete answer. This gives a complete answer that measure preservation or ergodicity means measure preservation or ergodicity on all factor sets, on all residue rings. This is equivalent. I'm not going to prove the theorem because the proof is quite involved, but this is an important theorem because actually we will prove the ergodicity or measure preservation, just proving that the corresponding mapping is bijective for all k, modulo pk for all k, or transitive modulo pk for all k, etc. Okay with this. Can I continue? Okay, is this clear? So
yes.
this, yeah, okay. Now, and now, well, it's the theorem remains true whenever the statement we change all k to all sufficiently large k, because one Lipschitz map, if it is bijective or balanced or transitive modulo pk plus 1, that it is balanced modulo or bijective or transitive modulo pk minus 1, etc., etc. It's clear. It is because of one Lipschitz. And the next proposition, which also is proved within the proof of this theorem, it's also important. A map is measure preserving and one Lipschitz, if and only if it is an isometry. It is an isometry. These are complete characteristics of isometries or one Lipschitz measure preserving maps. These are the same. Now we summarize. I give no proofs because all the proofs are a little bit involved. But now we summarize what about the dynamics of one Lipschitz maps. What does this mean? On one Lipschitz map, which are measure preserving, are isometries and vice versa. All measure preserving one Lipschitz maps have zero topological entropy. This, as topological entropy is in a way a maximum entropy, it's not less than, for example, Kolmogorov-Sinai entropy. This means they'll actually all entropies are zero, loosely speaking. All one Lipschitz ergodic maps are uniquely ergodic. This means that and every orbit of every one Lipschitz ergodic map is dense. These are what ergodicity and measure preservation for one Lipschitz, this for automata maps. This is a summary. And now what I'm going to do, if this is clear, if this statement is clear, I have no chance. It will take too much time to prove all this, but the proofs are given in my textbooks. They are lengthy, unfortunately. But if this is clear, then I proceed with giving examples and proving ergodicity of some interesting maps, which are one Lipschitz, thus automata maps. And the first one, which lies in a many we use in many cases as maybe a supplementary or additionally statement is these maps. This map A, B, periodic integers is an ergodic transformation on the P if and only if the following conditions hold simultaneously. This is not zero. this must be 1 modulo P if P is odd, and A must be 1 modulo 4 if P is 2. A little bit later, I will try to explain why this is a difference, but the proof is also not very short. And I have no possibility to prove it completely here. But I will make some hint a little bit later. These are affine maps, and this theorem is known at least from mid-30s and will use for computer scientists who deal with pseudo-random numbers. Maybe some of you heard about mixed congruential method of producing pseudo-random numbers. It is based exactly on this theorem, but because of certain problems, the pseudo-random numbers produced by this method are not good, because actually you see it is too simple and, so to say, too linear. Now the next step is we know that we can represent the function by Euler expansion. Any one Lipschitz map and every continuous map can be represented by Euler expansion, by Euler series. And the function define one Lipschitz measure preserving transformation on the P, if and only if A1 is not 0 modulo P, and the rest are 0 modulo P logarithm P to this power. And in the case P2, these conditions, these are sufficient conditions in a general case, but for the case P2, these conditions are also necessary. This is for measure preservation. I will give a proof, but in more general case. This is a sufficient conditions for ergodicity for P odd. The function defines a one Lipschitz ergodic transformation on the P when P odd, if the following condition, this is if conditions, not only if the following conditions hold simultaneous. These are. For P2, these conditions are also necessary. But the proof is difficult. The proof of necessity is difficult, and I will not give this. All these proofs are based. They use the following lemma. This lemma is also very important because it can be used to produce new ergodic or measure preserving one Lipschitz maps from a given one. For example, if this is an arbitrary one Lipschitz map, so an arbitrary automaton, and these are periodic integers with this satisfying these conditions, then this function preserve measure, and this function is ergodic. Delta E is a forward difference operator. I am going to prove this lemma, and from this lemma I will derive the sufficiency condition of ergodicity in terms of Euler series. So ready? I'm switching to proof. Now go to proof. What is so we only will prove the transitivity. We only will prove the transitivity of this mapping. So this is arbitrary one Lipschitz map. We will prove that if C is not 0 modulo P, that this map is also one Lipschitz. Of course, it is one Lipschitz as a composition of one Lipschitz map. Then it is ergodic. We prove this by induction on K. We will prove that is transitive modulo Pk for all K. according to our main theorem, this is enough. Well, modular P, we have that our mapping is just C plus X, and if C is not zero, this is of course transitive modular P. The iteration of adding non-zero element to any element results in a full cycle. So let H be transitive modular Pk minus 1. We will prove that H is transitive modular Pk. We will just calculate successively. We take the first iteration, right? Then we calculate the second iteration. But look how we calculate. If we calculate orderly this one, then by induction we can see that this is equal to this one. Then it is because of this we get this term. Then we get this term. We get this term and this term. So as a result, we have this one. Is this clear? Let's see the calculations. Just easy iteration. If this is clear, then we prove the following: for G equal to Pk to minus 1 to L, we prove this. We have proved this. This is the formula. But look here. Look here. Look here. By our assumption, H is transitive modular Pk. So when we iterate H from any point, this will, and iterate that many times, this will run modular Pk for all residues modular Pk. And this will also run all residues modular Pk. Maybe in some different order, but will run over all residues modular Pk. So this is a congruent modular Pk minus 1. Modular Pk minus 1. But here is P. So this term is zero modular Pk. And we get this one. And we get this one. But you see, this is where we will be after that many iteration of x, and we see that if as C is not zero modular P, then that many iterations of H from zero will be zero. If it is zero, then necessarily L must be zero modular P. This is a crucial moment. This means that if we have a cycle starting with zero, then the length of this cycle is P to power K. That's all. This means transitivity. Is this proof clear? Yes or no? Just simple calculations modular Pk and the transitivity. Clear, not? Can I continue?
Yes.
Clear.
Which
Okay.
is clear.
Clear. Okay, I continue. So having this in mind, we can now prove the if. So this is a if and only if condition of one Lipschitz in terms of Mahler series. I recall we have proved this. So this is f v is one Lipschitz. Then it can be represented like this. But we can then calculate this one and applying delta to binomial coefficient. We have this multiplying by P. We have this, right? So we have this expression for ergodic one Lipschitz map, and for ergodic one Lipschitz map. So look here, this is exactly what we get. This is the proof. Clear? Is this clear?
Yes.
So, okay. Okay, so we can proceed. Case P2 is much more involved. I cannot prove this. And, but it uses the following theorem, which I also want to mention because it is important. It's only for case P2, and this means that this is one Lipschitzness in terms of coordinate function. So every one Lipschitz map can be for P2 can be represented by this, and these are functions. These are this is the first digits of output. This is the second, the third, etc. And because of one Lipschitzness of automaticity, they had the following form. And this means these functions, they take only two values, 0 and 1, because we deal with P2, and these are Boolean functions. These are Boolean functions. Because these are also Boolean variables, and these are called coordinate functions. These are called coordinate functions. But every Boolean function can be represented in this form. This plus is addition modulo 2. This is called algebraic normal form. This is called algebraic normal form. And this is the theorem. This is the theorem which is known at least from 17th, but the author is not known. Everybody, well, at least everybody who deal with Boolean functions know the theorem, but nobody knows who is the author. So the function represented in this form and in the coordinate form P2 again. It is measure preserving if and only if each coordinate function is linear with respect to the highest variable, variable with the highest number. And this function is ergodic if additionally this function, this one is of odd weight. This means it takes on all Boolean vectors, it takes only odd number of ones, of odd number of ones, and this is equivalent to the condition that the degree of this Boolean, of this algebraic normal form is exactly E. I will not go to prove. I'm not going to prove the theorem because it's not very difficult, but it demands knowledge of Boolean functions which are outside of scope of our system. But what I want to demonstrate that you see the difficulty to obtain if and only if conditions for P not equal to 2 means that we need some rather difficult to check some rather difficult conditions of polynomials in multivariate polynomials over finite fields, and this is in many cases this is quite impossible. This is the following measure preservation ergodicity criteria in terms of van der Put series. Actually, this can be also by using this criterion. This criterion, folkloric criterion, can be proved. I am not going to prove this. I only say that this is known, and there are many other results. But only for p greater than 5, finding the ergodicity criteria, I mean the necessity condition, is looking absolutely hopeless. It's looking absolutely hopeless problem. For p5, there are results. Duran and Paco got ergodicity criterion for p3, but this is maybe this is the most people can do, and this is really difficult. But there are other useful criteria of measure preservation and ergodicity of one-Lipschitz maps for arbitrary p, but for narrow classes of functions, mostly of those which of these functions must satisfy some differentiability conditions, and we are going to discuss this condition. So I see that I have only 5 minutes left. Now I will only give a definition, an important definition of important notion of differentiability modulo pk, It differs. It is more general, just differentiability, but it is very useful. So we have one Lipschitz function. We have a one Lipschitz function. We say that it is differentiable modulo pk k fixed. At this point, if there exists a positive integer rational and a matrix, this matrix over p-adic integers, which we call the Jacobian matrix or modulo pk of these functions, so they point to such that every positive rational integer and every h, this congruence holds. This congruence holds. So we can obtain the value of the function. Well, we have an increment h that it can be expressed at the value of the function of this point plus this vector multiplied by a matrix. So this is linear linear transformation of this matrix and of this vector, and this depends on k, this k, and on u. Look here, modulo pk. So this means for this holds for some sufficiently large k. In other words, for some p-adically sufficiently small h. And these are the elements, the entries of this matrix are called partial derivatives modulo pk, and when m is 1, then m is 1, that is called the differential. It's only a vector. You may ask me, and this will be a good question, why? What is the difference? What is the difference with differentiability? The difference is that differentiability, ordinary differentiability, means differentiability modulo pk for all k, but this is sometimes an overkill in our studies, because in most cases one Lipschitz functions which are differentiable modulo p for k1 or modulo p2 for modulo p square is more than enough. We can prove a number of theorems which are true for functions which are differentiable modulo p or modulo p square, but which are not differentiable. Speaking loosely, the differentiability means that this fraction is approximately equal to derivative. Differentiability means that with arbitrarily high precision. But differentiability modulo Pm means that the precision must only not be worse than P minus n. This is the difference. This is an important notion, and this is the difference. This is the difference between two notions. This is purely p-adic notion. There are no such analogs in real analysis. The differentiability with precision of m digits after the comma, after the point is meaningless in real analysis. But here it is okay. Here in empiric analysis it is okay. So examples of functions. This function, for example, this function, P2 is, you see, it's XOR. This is addition modulo 2 to every coordinate of the base 2 representation of this number. It is differentiable everywhere on Z2. The derivative, I am finishing. The derivative is like that. But this function, this 3, and this is minus 1, 3. It is differentiable at no point, but it is differentiable modulo 2 at every point, and the derivative is 1. My time is over, so the next time we will start with this differentiability modulo pk, and I will prove some results concerning ergodicity and measure preservation criteria for functions which are differentiable modulo pk. My time is over. Thank you for your attention. If there are questions or comments, please ask me.
Thank you, Vladimir. Are there questions or comments? Okay, let's thank the speaker.
Okay.
Bye-bye. See you tomorrow.
Okay, so I am finishing. See you tomorrow. See you tomorrow. Thank you for your attention. I am switching off.
Bye. Para la grabación, now we have a break. So we come back at 11. Thank you. I cannot read it. ¿Puedes poner aquí? Pero bueno, no sé, a lo mejor es la conferencia. ¿Puedes poner aquí? Pues sí, aquí no, cuando empiece le tienes que dar a grabar, luego te va a salir aquí y tienes que ir admitiendo. Porque el hecho de que sea de libro una pregunta permite poner una serie de existencias siempre dependen solo de los I did the updates. It's super slow. ¿Sabes qué cosa quiero? No, ellos son más.
Okay, guys.
So, about exercises. Does exercise 2 even this exercise? I mean, you can send me the PDF. It's a email. I don't care. It's not computer. It's okay. You can send it.
Okay. Today we have the second part of the mini course on Introduction to Local Zeta Functions by Edwin Leon. Welcome, Edwin.
Thank you. Can you hear me, guys?
Yeah.
Okay.
Yes.
Let me share my screen. Can you see my presentation?
Yes.
Thanks.
Yes.
Okay, so today we continue with this crash course on local zeta functions. The goal of this session will be to prove, or better to understand a little bit. It was a theorem about the rationality of the local zeta function over the p-adic numbers. So the plan of this session of today will be to know what is the because okay, yesterday I mentioned that in order to show this, what Iglusa did in order to prove this theorem was to use a theorem of resolution of singularities by Ionaka. And this theorem is only available in characteristic 0. Okay. So we're going to try to illustrate this resolution theorem with some examples and some definitions. I hope that the definition, some of these definitions are very well known, but some of them are more hard to understand. But we will try to elucidate these ideas. So let me begin with this definition. We're going to need the definition of p-adic analytic manifold, and the best example for this is the p-adic projective plane. So this is something that this part of this text is part of the book by De Jong and Pfister, Local Analytic Geometry, and it is true also in this generality. So okay, let me just fix this screen. Okay. Okay. So every time that you see C, you can replace here C by K. I'm going to do this with red color. So you may replace this everywhere, this by K when Ks is a complete field, okay? So the projective space will be the set of lines in K squared, okay? Which pass through the origin. So in this case, we can replace this K with QP, for instance, okay? So another way of defining the projective space is to consider this relation, this equivalence relation defined over K squared minus the 0, minus the origin. And the relation, the equivalence relation is given by this symbol and is defined in this way. So 2 points here, they will be related if they differ by a scalar from a K, a non-zero scalar, okay? So an equivalence class of this projective space is just denoted by this symbol, or commonly this is what we use is this, is something like this, okay? So this is the same definition. So the only line that passes through to the point x, y, and 0 is given by these coordinates, okay? And these are called the homogeneous coordinates of P1. So let's see that we're going to define the following sets. So every time that I take a pair here, homogeneous coordinates on P1, if x is different from 0, then this is a special thing, and they belong to this set U1, okay? And on the other hand, I'm going to choose that the other coordinate will be different from 0. So this will be another set, and we have some morphisms here. There is a map from U1 to QP, defined by the quotient. This is well defined, and on the other set U2, we do the same thing but with Y. Okay. So by doing this, what we get is that these maps are actually homomorphic. Okay. And we can show that the composition of these two morphisms, and actually the composition of one of these morphisms and the inverse of the other, is an isomorphism between QP without the 0. Okay, or in general, this will be K, right? K without the 0. Okay. So what does this say about the projective space? So this is saying that in this way we have a cover of P1. Just think a little bit about this. This condition gives this, and this condition, they give all the elements in P1s. And moreover, we may equip P1 with a topology defined on every UI, on every open set. Those are open sets, so they will be open sets because I'm going to define a topology on the UIs that makes the following functions be continuous. Okay, the functions phi that I use to define these maps, I can ask that these maps be continuous. So this gives a topology over P1s, and in this way, P1s becomes a Hausdorff space. And with this definition, this is what is called a QP, in this case, a QP analytic manifold of dimension 1. More general, what we have is that a complex manifold, in this case, we don't need the word complex, just a manifold. You can replace this, for instance, by p-adic. A p-adic manifold is a topological Hausdorff space which has an open covering given by these guys, the UIs, and they are homeomorphic to an open subset of Kn. Okay, you may use here Kn or QPn, for instance. And instead of the phi's of these fi's, we are using phi's, and in such a way that every map of this way is a homomorphism, and these maps they glue in a good way, and by gluing in a good way, we mean this condition, that on the sets where they coincide, when the intersection of these two open sets is not empty, and this is well defined, this should be a holomorphic function. Okay. So this is the general definition for what is QP, or a p-adic analytic manifold in general. Okay. So the main example of a p-adic analytic manifold is the blow up. Is the p-adic space is P1, and we are going to construct another example of another manifold, and this manifold will be called the blow up or the blowing up of 0 of the origin in k squared, right? So remember that we were saying that we may replace everywhere here C by K, okay? Or if you prefer, you may replace this by QP, right? So what is the definition of the blow up? For the definition of the blow up at 0, I'm going to use these guys, the charts that sorry. Usually a set like this, a couple of the form UI, CI, this is called a chart, okay? This is called a chart. Okay, so I'm going to use the charts, my charts, in order to define this as a p-adic analytic manifold. So the first definition that I want to give is a very intuitive definition. So I'm going to define the blow up by taking pairs, and in the first coordinate, I'm going to take a point of C2. You may think that this is QP squared, for instance, and then we're going to take in the other coordinate a line passing by this point and the origin. Remember that those lines belong to P1 just by definition, okay? So the blow up is just the set of pairs consisting of lines and points and lines passing through that point and the origin, okay? So there is a natural map, the projection map, that is considered the projection on the first coordinate, okay? Remember that everywhere you may replace this by QP. This has exactly the same meaning, okay? So we have a definition. The thing is that for points, if we take a point that is different from 0, then there is exactly one element in the inverse image of that point, okay? Because there is just one point passing through P and 0, right? But if you consider the inverse image of the 0 through this map, what you will get is the whole P1, because those are the lines passing through the origin. Okay, so all the lines passing through the origin, they define P1. Okay, so this P minus 1 of 0 has a name, and this is called a exceptional device. Okay, we can describe this set in coordinates, and actually the coordinates for this set, they say this exactly the same thing that we were just discussing, so I'm going to skip this. So let me give you the charts of these guys. So remember that we have that P1 equals to U1 and then U2. So we have that the blow up of, I'm going to write this in this way. This is times U1. This is just a set of coordinates or the following way: x will be, and then you consider, because we are in U1, and in U1 the first coordinate is not 0, so you may assume that this coordinate is 1. So you consider the pairs of this form when x and b are elements of QP. Okay. Okay. So this is isomorphic to QP squared with coordinates x and b. Okay. So on the other hand, when we use the other chart of P1, what we have is the set of coordinates of the form y, u, y, and then the point in the projective space is u and then 1, because in this chart the second coordinate is different from 0 for any y and u QP. So this is again isomorphic to QP with coordinates, to QP squared with coordinates y and u. So this is also a description in local coordinates, or in local charts, if you want, of the blow up of QP squared. So this defines exactly in the same way that we saw before. You can prove, I mean, you can construct these maps and check that this definition is okay for these charts. So this set is also a p-adic analytic manifold. Okay. Okay. So we have p-adic analytic manifolds, and now I need a very special map between p-adic analytic manifolds. Okay. So I'm going to use, oh, sorry. I don't know what's going on. Sorry. Okay. Okay. So I'm going to consider a polynomial in QP, right? So for the set of zeros of my polynomial, I am going to use the set B. So the closure of this of P minus 1 of this set is called the strict transform of the map P, and the whole image of P minus 1 of P is called the total transform. Okay. So let us consider a couple of examples in order to put our hands on and try to figure it out what all these definitions mean and how we can use it. So the first example is very simple one. We are going to consider just a function that is given by a line, okay? So what we do when we want to compute, we blow up at the origin of this line. So what we need to do is to choose a chart. Right? By choosing a chart, I'm going to use new coordinates, right? Because remember that we have here a couple of coordinates, x, b, and here coordinates y, u, and this coordinates says that what is the change of variables that I need to make, okay? So in practice, what we do is that we change variables in this way, and then we will see what happens with the function f. Okay, so let me write this way. So what happens with the function f is that instead of y, I write x d, and instead of x, I write again x, okay? So this is just x times b minus a, right? So this is called, this guy is exactly, so this whole thing, let me just do this. This whole thing is called the total transform and notice, we have to notice that what is the inverse image of every point, I mean, what is the inverse image of 0? So we have here pi minus 1 of xy, and if this is equivalent to compute pi minus y of xb, if this is 0, this means this is 0 if and only if x is equal to 0, right? Because this is the point that goes to 0. So this is called exceptional divisor. Those are just names. Don't worry about that. Okay. So the thing that appears here. So this is 0 when x equals 0 or b minus a is 0, right? So when x equals 0, this is equivalent to compute the inverse image of 0. So this is called the exceptional divisor. And what we have is that that the total transform, another way to write the total transform of B is by using this notation. So the exceptional divisor is usually denoted by A. So what we are saying here is that this exceptional divisor corresponds exactly to this x, okay? And the other set this B minus A is this set, okay? So what we do is that we try to represent this situation in a diagram like this. So you may think that this is QP squared. So there is a line with equation y minus ax. So this is the line f, or f equals 0. I'm going to use, instead of this, I'm going to use b. So b is given by this line, and my map pi, I'm going to try to represent in a graphic this situation, okay? So because the local equation for E is given by x equals 0, I'm going to represent this by a line. So I'm going to use this line in order to represent E. And this other thing that appears here, I'm going to use a different color. Let me use this way. So this is a line corresponding to E. And for the other component, I'm going to use something like this, because the equation of this line is exactly B minus A. Okay, so they should put in this normal form. Okay, so okay, this is with a lot of technical definitions. This is what we understand by the blow up of a line. So I want to notice that, okay, no, I'm just going to skip this. So a more complicated example, a little bit more, is given by the following guy. So if we consider this equation, we can use the same approach, and then we make these change variables, and we get what we get is something like this. And we can compute from these equations the total transform and try to represent these equations in this way. So, but what I want to notice is that what we have here, a map pi that is a resolution of, that is a blow up. What a blow up does is that separate lines. So these are lines that are passing through the origin, and these three lines, they are separated in three components here. Okay, and so every time that I blow up one point, in this case I'm blowing up the origin, I get a new guy that this is called a divisor, and the question, what, and this guy comes with some data, and I'm going to give you more details later. Okay, but the thing is that I just want to, okay, yeah, sorry, let me just mention this other example. This is something that we saw yesterday. So we have the cusp singularity. Yeah, the drawing of the cusp is something like this. So when you apply this process of solution of singularities, of blow-ups, what you have in the first stage is that this, because this is a different curve, okay? So what you have in the first stage is that there appears some guy that corresponds to the blowout of this point, and then the curve is transformed in this one, and we repeat the process because what we want to have is something like this, where all the crossings are normal crossings, right? So in order to obtain something like this, we keep doing this process. So we repeat the process again, and then what we have is something like this, and we need to blow up again the origin in order to obtain something like this. So the final configuration looks like this, okay? This is a little bit technical, but I don't want to go into the details. I just want to mention that this construction is interesting, is useful, and maybe we can understand a little bit of how these things work. But of course, my advice is to consult some reference, some specialized reference, if you want to get acquainted with this material. Okay, something like this will be okay. Begin with. Okay, so in general, so what is the point of mention all this stuff? Because we are trying to describe p-adic analytic manifolds, because that is the ambient space of the Iguza's theorem. So we need to understand not just p-adic manifolds, but also maps between p-adic manifolds, okay? So, and especially we are going to consider this map. This map will be really special, the blow up map, okay? So p-adic varieties, p-adic manifolds are something really useful, and there is a couple of things that make or characterize p-adic manifolds versus the classic, for instance, complex manifolds or real analytic manifolds, okay? So essentially, from an informal point of view, you may think that an analytic manifold is a Hausdorff topological space that locally looks like the union of these guys, because in general, a complex analytic manifold is just locally looks like the union of open balls of dimension n, of some open set of dimension n. So in this case, this is also true, but in this case, remember that the open balls of dimension n are guys like this, okay? So you may think informally that a p-adic analytic manifold is a topological space that locally looks like this. And by locally, I mean you need all this material. In particular, you will need the definition of the functions or of the coordinate functions, right? Okay. So far, this is like in the classical case of the compact this is very similar to the complex, for instance, to complex analytic manifolds. If you have encountered these objects before in your courses, you couldn't notice the difference between those guys. But there is something. So what I mean is that there is no real difference between any p-adic between consider a complex analytic space, for instance, or a p-adic analytic space. You are not using the topology in order to define the structure of analytic manifold. Okay. So what is really when really enters the structure of the p-adic sets is in the following theorem. So the first interesting, or let's say different result about the p-adic analytic manifolds is the following Serre's structural theorem. So this is a result that says that if you have a compact I don't know what it's a compact analytic, if you want to add this compact QP analytic n-dimensional manifold, then X is isomorphic to the disjoint union of R times CPN for a unique R between 1 and P minus 1. So this is something that is really, really special about the p-adic world. In the p-adic world, the compact analytic manifolds are the very few. Okay? If you have a compact analytic manifold, p-adic manifold, you essentially have CP to the n, or 2 times CP to the n, or 3 times CP to the n, or P minus 1, or dots, P minus 1 times CP to the n. Okay, so this condition of compactness is really strong, and this is something that is unique from the non-Archimedean case. Okay, so we are going to use this later in our definition. Okay, let me mention what is a differential, or how the differential forms look like in a p-adic analytic manifold, or more precisely, I want to mention this result that is also true in the complex case, for instance. So when we have in a p-adic analytic manifold of dimension n, when one associates a measure to a given analytic form of degree n, for example, a hard measure dx. Wilson uses this one like in order to differentiate between the differential form and the measure. This should be, I mean, a correct way of say this is the measure associated. The differential form. Dx wedge dx2 wedge dx. Okay. Every time that I have a differential form, I have automatically, or I can associate a measure to this guy. Okay, so those are the ingredients for the following Hironaka's theorem. So I'm going to just remind you that this version of Hironaka's theorem is in our paper, and the notes are available on the webpage of the conference. So I'm going to just to read the definitions, and I'm going to try to highlight what is necessary here. So this is the theorem about resolution of singularities. Okay. So resolution of singularities, I mean, the philosophy behind this is that every time that you have a singular variety, or a singular manifold, you may replace this manifold with another manifold without singular points. And this replacement has some restrictions, and the new variety that you build is something that you can handle in some ways. So, yeah.
A question.
Sorry. Yeah.
Is there a way to replacement?
Sorry, can you repeat the question, because I didn't hear well?
Is there an unique way to make the replacement of the singular manifold?
To make the replacement of what?
Of the manifold is a unique. So, well,
I don't understand what you mean by replacement. I mean, are you talking about the resolution of singularities? If there is just one manifold that is going to replace the singular manifold that I was talking about? So for the answer for that question is no. So there is no a unique way of doing this. So this process is not unique. I mean, it's just, it has some minimal version in the case of in dimension 2. But in general, this process is not unique.
Okay.
Does that answer your question?
Yes, yes.
Okay. Okay, so I'm going to try to explain a little bit of this definition, okay, of this statement. So we start with a polynomial function in QP. So the thing is that it is possible there exists a manifold Y and a finite set of closed submanifolds. By closed submanifolds, remember that I was using this letter E for something that is that was in our examples a P1. Okay. Remember that in our cases This is something that is called a P1. And maybe do you remember that when we were using QP squared and the blow-up map, so this has dimension 1. So a closed submanifold of codimension 1 can be understood in some sense I mean, in the case of n equals 2, is just a collection of P1s, okay? So let us continue with this. So in general, they can be more big manifolds, but they will be like copies of, you may think in these guys of copies of P1s, okay? At least in the case of dimension 2. Okay, yeah. I'm not going to say anything else about this. So the thing is that every manifold of this, every submanifold of this way, of this form, has some numerical data assigned, okay? I'm not going to explain this at this moment. I'm going to give you some examples later, okay? But each manifold here has some numerical data. These data are positive integers, okay? Okay, but let's continue. So the theorem says there exists a manifold Y, and there exists also a map. In this case, the map is called Y, it's called H, sorry. And there exists also a map from Y to QPN, okay? And this map and this manifold, they satisfy the following conditions. First, H is the composition of a finite number of monoidal transformations. What are monoidal transformations? Are just generalizations in several variables of blow-ups, okay? You may think as this being finite compositions of blow-ups, okay? For instance, like what we show when I show you the cusp singularity and the resolution process of the cusp singularity. So this is the first condition. For the second condition, what we have is that the inverse image of f to the minus 1 is exactly the set of closed submanifolds that we pick at the beginning. So this guy. So in our examples, this was just a collection of P1s. Is P1s, I'm going to say P1s, and then I'm going to use the subscript here, P1, T1, and there is also another P1s, okay, or something like that. Okay. But what we have is that this function, this map H, is also a p-adic b-analytic map outside the singular set of QP, of F, sorry. So outside the singular set, this is like an isomorphism, okay? So this will be very important later. Okay, so are those conditions clear? So the final condition is that it is possible to have local equations and local descriptions for everything that I'm going to use in the manifold Y. So remember that in our case, we have, like, for instance, that this was the blow up. The blow up was equals to the blow up of QP squared was equals to the union of two charts. Do you remember? I'm going to call this U hat 1 and U hat 2, okay? Two charts. So in each chart, I have, for instance, in this chart, I have these coordinates, and in the other one, I have the coordinates Y and U. On U and Y, I don't remember the order, but the local description in each chart is given by a monomial or something like this. So in general, when you do this process in general, what we have is that the local description of the preimage of these guys is a monomial and the powers appearing in this monomial are exactly the numbers that I'm going to use as a data attached to every variety, every manifold here. So let's go back to our example, and we take this blow up, or variety Y is just a collection of P1s. So every guy of this form is a P1. So every one of this form is a P1. In every local chart, I have something, I have like a X to some power, okay? And this power is called the data attached to this P1. So we have an expression, a very explicit expression for this composition, okay? But we also have a very explicit expression for the what is called the pullback of the differential form. You will see in the examples that this is something that appears when you use this as a change of variables. You can use the resolution of singularities map as a change of variables, and then this is the thing that appears like the Jacobian of the map P or H. We are using H in this context, in the variable Y. So at this point, maybe this is not so clear, but I hope to show you a couple of examples of this process using these definitions, and maybe you can understand a little bit better this statement of Ironak's theorem. So if you want to take a break now, so we can make it. I mean, we can take a break and come back in 10 minutes. Is that okay?
Okay.
Okay. So
Let's take a break of 10 minutes.
Let's take a break on 10 minutes and then we continue.
12:05. We come back. So.
¿Ah? No. Ya ve que define la acción del operador.
Sí.
¿Hay resultados interesantes relacionados con esa acción?
No he visto nada. digamos, ese artículo, la parte más, yo no sé si ese operador funcione bien, ¿no? Lo que pasa es que sí lo construyó. Pero una cosa que sí es interesante es que los muebles de Pusir se pueden poner en correspondencia con los muebles de Hart. Esa es la parte, eso es muy interesante. Pero yo de este operador no he visto nada, o sea, es una pregunta interesante, si se puede realmente hacer algo interesante.
Sí, porque al final de cuentas
pero alguna vez estuvimos tratando de hacer algo y no nos funcionó. Me acuerdo, porque si alguna vez tratamos de hacer algo con eso y no nos funcionó. Porque hay una dirección que es la que más conviene y esa es la que no está disponible. Ya no me acuerdo. Si alguna vez, y hay, sí, porque hay.
Sí, porque lo que hace es agarrar a las dos internas a las de construcción.
Sí, hay que mirar el problema. Yo me acuerdo que estuvimos tratando de hacerlo y hay una dirección que la que no se puede hacer. O sea, hay que pensar que lo que uno quiere, o sea, si mover algo de los creadores, reales o viceversa, tal vez era algo real a los creadores. Pero no me acuerdo. Pero alguna vez intenté y no, realmente no lo vimos no logramos aplicarlo. Pero estaba interesante. Y lo otro sí que es muy interesante es que los juegues ponen correspondencia.
Sí. Gracias. Sí, tenía algo hacia allí.
No, de eso no he visto ningún resultado. Ah. Rogelio, activa.
Okay. Okay. So I move this example here. Shall we continue? Are you ready, guys?
Yes, we are ready.
Okay. So I move this example here because I think this is worth to take a look again. So you remember this example? We had 3 lines, and these 3 lines, we applied to these 3 lines a blow up. So what we obtained was something like this. What is appearing here is a map, is a line that is isomorphic to a P1, and then there are other three guys. But what I want to highlight is that the set of closed submanifolds is given in this case just by this line, by this guy. So in this case, this whole configuration, this whole configuration will be my space Y, okay? So this will be my space Y. And we are doing this in QP square. So we have a map from Y to QP square. This is the map H. And we have on the right hand side, we have a manifold, because we already showed that the blow up is a manifold. And we're going to check is that all this definition makes sense, okay? So the first thing is that this should be, so what are the, sorry, let me see what I want to say. Okay, let us use this definition first. So maybe do you remember that when we were doing these calculations, we were saying that this guy E has a local equation given by x equals to 0. And why is this? Why is this true? Because we use this change of variables, okay, in order to construct or chart. And this is just the first chart, okay, of the p-adic analytic manifold. So the local equation for this guy is x equals 0, right? So what is the this means that this x equals 0 is equivalent to this y I appearing here. This yi is equivalent to this x. And this 3 appearing here is exactly the ni corresponding to this. But this is just one guy, okay? In this case, there are no m guys. We just have one guy, okay? So what about these guys? What about the differential form? So the differential form comes because you can think about the following form, dx dy, and how is this form transformed through this change of variables. So you need to compute, instead of x, you write x, and instead of y, you write xv, okay? So when you do this, what you get is, I'm not want to do this in the, it is dx, and then you have here dx, p dx plus x dv, right? And then what do you get here? This cancels out with this one, and you get x dx wedge dv, right? So this is a monomial times the new differential form. So you're just computing like something like the Jacobian through this to this change of variables. Okay. So this is what is appearing here in this as these exponents, they are the exponents appearing here. Okay, it's something like that. Okay, so we are going to, with this example, I hope that some of these definition are clear, more or less clear. So we are ready for Iguza's theorem about resolution of singularities. So Iguza's theorem says the following. In a more precise way, they say, the theorem says, Iguza's zeta function is a rational function of, in the variable p to the minus s, and this implies that it has a meromorphic continuation to the whole C. Okay, so remember that a meromorphic continuation means that your function as a complex function has poles. Okay, so but this is even stronger, because you are saying that your function is a rational function. So when you have a rational function, you want to know what is the numerator and the denominator. The denominator in this case can be known. I mean, we can give you the denominator, but so what are the things appearing here in the denominator? The things appearing here, let me just use this. So we are assuming all the terminology here. So this data, the things that appear in the denominator are just factors of 1 minus p to the minus nys plus bj. So those are the numerical data. Remember that the data, these are the numerical data associated to a divisor, to some A. Okay, so the poles of our zeta function are given by the numerical data of each divisor. Moreover, we can see that the zeta function has poles of order at most n, when n is the dimension of the ambient space. Moreover, we can describe exactly, or we can give a list of possible poles for this zeta function. So the possible poles, they have this form. Because every exponent of this form can every exponent of this form, when S take this form, this can be 0. Okay, so this can be 1, and then this denominator will be 0. Okay. Okay, so I'm going to give you just one example, and I hope that this example illustrates the power of this statement. And then we are going to discuss a little bit the proof of this theorem. Okay. So for what I want to do is to take this example. So let me see if I can do this. So my zeta function will be x, y, x minus y, right? So I'm going to compute this integral. By using this method, right? Okay. So the first thing that we're going to use is we are going to use this map H. Sometimes I call this pi. This map will be used as a change of variables. And how does this work? Why I can do that? Because remember that outside the singular set, H is an isomorphism. Okay, it's a PIDB analytic map. So this means that I can use my map H as a change of variables. Okay, outside the singular set of set function. So I can write this. Remember that I can take out this without any harm, and then my integral is exactly p minus 1 of Cp squared. And then you may think about this, taking out this quotient, this other set or not. I just going to use this writing, okay? Because I don't want to write the whole thing. So the point is that I need a description of this. I'm going to use this pi. Let's take this. Okay. So if I want to use this as a change of variables, I'm going to need this. I'm going to need here f composed with p, with pi, and the coordinates y, then to the power s, and then there will be the Jacobian of my pi, the variables y, then something like this. Okay, this is very general, but I want to make this more clear. So the thing that I'm going to do is to I'm going to look for a precise description of this set pi minus 1 of Cp squared. So I need a good description of this. And in order to do that, I'm going to separate Cp in the following way. So this is the set of pairs in such a way that we have the periodic order of y greater than the p-adic order of x, and this is greater or equal 0. This is the first set. And for the second set, the condition is that the order of y is less than the order of x. So it is not difficult to see that this actually gives a partition of Cp squared, okay? And then pi to the -1 of Cp squared can be given as the disjoint union of these two sets. So why this is true? Remember that we have local descriptions for pi. So in the first chart, change of variables was x equals x, and y equals x b. Do you remember this? So if I want to see how b should be, I can write this in this way. So from this equation, I can write b as the quotient of y by x. So if you want to compute the order of b, the order of b is exactly the order of y minus the p-adic order of x. Okay? So you need a set that describes properly or describes in a good way these relationships, and this is exactly this set. Okay? So for the other set, what we are saying, what we are using is the other chart. Okay, I'm not going to do all the details, but in this case, you remember that the coordinates, the change of coordinates that we are doing here is something like this. So we have another description for you. Okay. So this is in the other chart. Okay. So this first set. So this first set goes through the inverse image of pi in this set, and the other one goes through the inverse image to this set. Okay, and you can check the details as an exercise. But what this is saying is that my integral is now over this set, becomes the integral over Cp squared plus a integral over Cp times Pcp. So in the first chart, the thing corresponding to this first chart is just these local equations. So my local equations in this chart are these ones, right? So I'm I have to use this. X cube B and then 1 minus B. Okay. This is PS. And then I need to compute the Jacobian. Okay, the Jacobian of this change of variables, but I already do this here. So I'm going to put here X and then dx dB, right? So we just did this change of variables in the first chart, but we are not seeing the second chart. We didn't do that calculations, but in the second chart, what you get is something like this. For the function, you get y squared u minus 1 ps. For the Jacobian, you obtain this y and then dy du. So look, what we have done here is that I begin with an integral over Cp, and then I'm using all this information given by the resolution of this blow up. This is just a particular example of a resolution of singularities. And using this information, I was able to change my integral for an integral with an integral that is defined over these two sets. Actually there are two integrals. So let us see if something is more easy to compute. Okay. So for this first integral, actually I'm going to use just the first one. So for this integral, we know that this term appearing here is a unit, right? So the unit of this guy, so this being a unit means that the norm of this guy is 1, okay? So this behaves essentially like the monomial x the cube b. And we know how to compute these integrals because they have a very explicit equation. So I think we already saw this calculation yesterday, but I'm not sure. But the thing is that this integral is equal to the integral.
Sorry.
Yeah?
A question.
Yeah.
I think 1 minus b is not a unit because b is in CP, so it can be 1, for example.
Oh, yeah. Sure. Yeah.
I think the one that is a unit is the other one because it's in PCP.
Yeah. I'm sorry about that. Yeah, you are right. Yeah, I was thinking in the other case. Yeah, it is true. B can be 1. So in order to compute this integral, you can split this integral in two cases. So in the first case, so you need to split the domain of integration in two sets. X is just a point in CP, and B is a point in the following set: CP minus 1, and then the other set will be X in CP and P in the set 1. Okay. So in this case, this is clear, but in the other case, what we have here is that you can compute this integral, and this is something like you can use this formula that we saw yesterday for this integral, right? So this behaves something. This is something like this times this integral over CP. This other integral over CP. This is not CP squared here, it's just CP. And this is B1 minus B here. Yeah, you're right. This is something that we have to do very carefully. So you can use this trick in order to compute this integral, or you can use, for instance, the stationary phase formula, okay? So if you have not exercised, you can do this in the exercise session this afternoon if you want to try, for instance. But anyway, what I want to say is that this integral is actually more easy to calculate than the integral that we begin with, okay? So the point is that by using resolution of singularities, by using the process of blowing up, we may change or integral for something that is more easy to compute, okay? So the other integral is similar to this one. You only need to take care about the second variable here, u, because u is in PZP, okay? So you may change. What we do is just a typical change of variables, and then you make all the computations. So after as an exercise, you can check, let's say, first exercise. So the a second exercise for this session will be to compute the final form of this integral. The final form is p pi p minus 1, and then p minus 3s 1 minus pi p minus 1 minus s 2 minus 3s, and then we have a different numerator. So this illustrates how the process of blowing up, or in general the process of resolution of singularities, how this process can be used to compute integrals, to compute local zeta functions. So what the important thing about this theorem is that Igusa is able to control the whole process. I mean, not Igusa, Hironaka is able to control, because this is just one blow up, and blow ups are very easy examples of resolution of singularities. But when the size of the ambient space increases, this process of resolution of singularities grows like in a very, very bad way. So the difficulty of the process increases a lot. So this process of resolution of singularities is actually really, really complicated, okay? So it's really hard to track all the change of variables, all the charts that you are doing, and the whole thing is really complicated. There are some implementations, for instance, of this resolution of singularities process in 3 variables in singular, for instance, but they are not very efficient. I mean, it depends of the polynomial that you are taking, but in general, the task is really challenging. Okay. So this process, in general, requires a very good control of the singularities through the whole process. So it's very complicated in general. But what the GUSA does here is to show us that using this process, uses this change of variables, using just this idea, we may reduce the computation of something that can be very complicated in this at the beginning, and we may reduce the computation to some polynomials, to some monomial equations, sorry, to some monomials, to the integration of some monomials. So let me show you a sketch of the proof of this result by GUSA. So what is the idea? The idea is to more or less to do the same thing that we did in the previous example, but in a more general way. So the thing is that Hironaka's theorem says that a resolution of singularities, by a resolution of singularities, we understand a pair with the manifold Y and then the map pi. Okay. So the resolution of singularities has this property that this map is a B-analytic equivalent outside this set, so outside this set, and this allow us to use pi as an honest change of variables. Okay, so we use this in order to tackle this integral. We use pi as a change of variables, and what we have to do is to compute all these guys, right? Because this is what the theorem of change of variables says. If you remember from the lecture of Wilson or Trond, change of variables looks like this. So we need to compute all this stuff, but we need to work over a special set. What we did in our example is to describe explicitly in each chart this set, how this set looks like. Okay, and this is really difficult in general. So this trick that we did here doesn't work very well in several variables, but instead of that, we are going to use a powerful theorem. So instead of doing that, what I'm going to do is to use that the map pi is a proper map. So what does that mean, that pi is a proper map. It means that the inverse image of compact sets is also compact. So pi to the -1 of CPN is a compact set. Why? Because pi is proper and CP is compact. Okay? So this is the definition of the properness. The definition says that the inverse image of a compact set is also a compact set. So in the p-adic case, we have Serre's theorem saying that a compact p-adic manifold is a copy of CPN sets. Do you remember this? This is R times CPNs. Okay.
Where R is between 0 and P1. P
Uh-huh.
1.
Yeah. That is why that is what Serre's theorem says. So I'm going to use this fact. Okay, but first let me because I have this another line, and for this line, this is just I just want to make a comment about this. So here, what we have here is that we have a function depending on y and s. Okay, this is the Jacobian. This is a function depending on y. So this is a function multiplied by dy, and this function defines a differential form. Okay, and this differential form gives a measure, and this measure is denoted by this in this way. Okay. So this is the only comment that I have about that, and this is the reason for this line. Okay, so by using Serre's theorem, we are left with this. Let me go back to my notes. So more generally, I'm going to assume. We are going to assume that pi -1 of CPN is a disjoint union of balls of the form P E Z P to the end. Okay. So instead of this, more generally, balls where the radius is changing of this way, for instance. Okay. So I have to do this integral, and I'm going to replace the set of the domain of integration by this product. Okay. Okay. So what we have, what we need now is an explicit description for this guy, right? I need an explicit description for this guy, and then another description for this one. But they are given in Hironaka's theorem. You know, maybe you don't remember this, but we have an explicit description for this guy. Remember that I'm using pi instead of h. So we have a description for the composition of f with pi, and also a description for the pullback of the differential form. Okay, I'm going to use this color for this guy. So this is the green guy, okay? So in this chart, so the pink guy here, oh, sorry. So the pink guy here is a monomial. It's the product of monomials and I and then units and that's all. Okay, so this pink guy here correspond to this pink guy here. Okay, now the pullback of the differential form is also a monomial, a unit, and then a monomial, but now the power is ej minus 1 p s dy. Okay, let me put this. J is between 1 and r. J is between 1 and r. And this is exactly the green guy. Okay. So there's descriptions. These descriptions they come from Igusa's theorem. Sorry, from Hironaka's theorem, right? So they are coming from these expressions. Okay. So now we have to compute this. So the first thing that we have to note is that, okay, this is equivalent to this integral Cp here, then the unit Es and the other unit without S, and then the product of monomials, absolute value of monomials, and the power is, in this case, n j s plus nu j minus 1, okay, dy. Okay. So the thing is, we need to treat these guys, but we may assume that we are working on a sufficiently small ball in order to make these guys constant, okay? Because I want these guys out of my integral, so I can use smaller balls if needed in order to not to consider these guys. So at the end, what I need to do is to compute, because this is a constant, this goes here out of the integral. So I just need to compute the integral of these monomials. Okay, but the integrals of these monomials are very easy. I don't remember exactly if we did it last time, yesterday, but if not, they are just generalizations of our previous work. So I just want to write the following formula, and you can check this in the exercise session. So I'm sorry for not to make all the calculations, but it will take more time that I have. So this is the thing that comes because when you change, when you perform the change of variables, because y is in a ball like this, so you change variables, like instead of y, you write p to the a j c, for instance, or something like that, and then this is what comes out of the integral, okay? And then p minus aj, this is because that change of variables, and then the measure of the ball that is given by this. And there are also other sets, because notice that this product is over J here, runs through the set 1 and n, okay? And here we are taking the integral because another parameter that is r. So we are doing just other calculations. So for the remaining terms, we have something like here, something like this one, because we don't have variables here. So what we have is just the measure of the balls here. And that's it. I mean, what our purpose was to see that the integral is a rational function of p to the minus s, and this is the rational function that we were looking for. So I'm not going to check the details, but you can check in my notes, in our notes, or in the exercise sessions, that the poles of the local zeta functions that appear here in our calculation were exactly these guys. Okay, I mean, you can see there, if you look carefully, you can see there here. So I want so this ends with the proof of Igusa, but I want to make a couple of comments. First, the guys that we have here, they are called candidate poles, and they are called candidate poles because in general, you don't have to, in general, they might not be poles because there is some cancellation problems. What the theorem says is that your denominator is something like this, but you don't know anything about the numerator. So it may happen that in the numerator appears something like this, and then this term cancels out, okay? And that fact, that phenomenon is more common that we expect. So in general, there are a lot of cancellations, and determine the true poles of the local zeta function is a really interesting and difficult open problem. Okay, so determine the true poles of the periodic zeta function is a very challenging problem. One of the things that we can, one approach that we can have to this problem, for instance, is to use what is called the geometric determinations of the poles. By the geometric determination, I mean every pole comes or appears as appears because there is one data. Do you remember that there was, these guys are the numerical data and they're coming from one exceptional divisor here in the resolution process. So the geometric determination of the poles looks for conditions over this process of resolution of singularities, because there are some cancellation problems, and what we need to know what which of these guys contributes a pole, if these guys have some special properties or something like that. And this is a very active research area, okay? And this has a lot to do with also with another topics and other things in singularity theory. For instance, one of the main topics here is the monodromy conjecture. That is a very relevant and open problem in singularity theory, and I would say in algebraic geometry in general. Okay, so finally, I want to comment that there is a special relationship with the largest part, real part of the pole of the local zeta function. Let me call this guy sigma. This guy is also called in another in algebraic geometry. This is called the log canonical threshold. So the smallest pole of the local zeta function is the log canonical threshold. And for instance, with respect to our sequence Nj that we saw yesterday, we have that the following result. So the asymptotic behavior of these guys are controlled by the log canonical threshold of the local zeta function. So this might be another interesting feature in order to compute poles of the local zeta function, for instance, because they are useful in number theory when you want to estimate the behavior of this sequence. Okay, so my time is over. So if you have any questions or comments, I can take it now.
Are there comments or questions? Okay, then let's thank to the speaker. Okay, now we have the lunch break. We are supposed to come back to 3 p.m. Yes. Okay, bye, Edwin.
Okay. See you guys. See you later.
¿Pagaste la grabación? El soporte a ella, yo creo el soporte es como pago.
Tiene un problema de cambio variable. Pero todavía no sabes si es un mapa.
Cambio de variable.
Y la
Probando. Probando 1, 2, 3. 1, 2, 3. ¿Se escucha mejor? Hola, hola. Probando 1, 2, 3. 1, 2, 3, 4, 5, 6. Sí. Es que es eso.
Moris Rojas, estás aquí. Moris Rojas.
Joseph J.
Maurice Rojas.
That's natural. That's not something in Spanish. To translate that in English. The way that it's said out, that's very different. I wouldn't use the translation, the exact translation. I say that in a similar way. So it's more natural for me.
¿Me dices que se conecte ya?
Maurice Rojas, are you there?
I'm here. I'm waiting for you guys. I'm here.
Can you please connect?
What?
Can you please connect your slides?
I'm connected already. I'm here.
Hola, Maurice, ¿cómo estás?
Bien, ¿cómo estás?
Bien. No, ya preocupado, si nos perdió el speaker.
Sí, no, estoy aquí, estoy mirando dónde coloco mi audífono. No lo veo, creo que está en otro lado. Aquí está. ¿Alguien tiene parece que el micrófono prendido con los audífonos o algo de parlante? Hay una conexión doble, algo así.
No, en español. Sí, pero...
I'll give the talk in English, but you know, I'm happy either way.
You can listen to me.
Because I don't know if you can hear me.
So,
Can I share the screen?
no, we are not seeing
Yeah,
the screen.
please.
Can I share it? Okay, I'm asking for
Yeah,
permission.
sure.
Okay, good. Okay, can you see it now?
Yes.
Yeah.
Okay, good.
Okay, ready?
Yeah, I'm ready.
Let us begin, Roger. Good afternoon. It is a pleasure to introduce Professor Maurice Rojas. Okay, I'm going to repeat it. It is a pleasure to introduce Professor Maurice Rojas, professor of Texas A&M University. Professor Rojas is going to talk about an overview of p-adic algorithmic phenomenal theory. Welcome.
Thank you. Thank you. So there's a lot to talk about, and I'm probably not going to be able to talk about everything I want to, but I'll try to speak about as much as I can. I'm hearing some audio. Can people please mute? I hear like a lot of noise. There seems to be some strange noise. Okay. Okay. Well,
we are not hearing any noise here.
Okay. Okay. Well, anyways,
I think it's just the noise of the room because you know it's
okay.
of the audience. So
okay, that's good. So anyways, where is everybody? Is everybody in the F in the Distrito Federal de Mexico? Is that where the conference?
Actually, the school is in Guanajuato.
Guanajuato. Okay. I was confused because I tried CMAT on Google and it showed up the F. Okay, so let me start with the results. Let's begin with a theorem over the complex numbers. And so I want to start with this theorem over the complex numbers because it's a really beautiful theorem and it has a lot of sort of p-adic elements to it, even though you don't know they're p-adic. So I'm going to call this the Wilder-Verhev theorem. And it's a theorem which is quite beautiful and deserves to be better known. And this theorem comes from Wilder's portion comes from 1917, and the Verhev portion comes from 1977. And I do want to point out that Mark Verhev, he's a very sharp computer scientist, and it's not the first time that a computer scientist has done some really great mathematics that we should learn from. So the theorem goes as follows. It's a result for roots of polynomials in one variable, which takes into account the structure of a polynomial in a fine way. So let's suppose you have a polynomial in one variable, and let's suppose I'll allow Laurent polynomials. So this means that I'll allow negative exponents as well. That's what the notation means. And let's suppose it can be written this way. Suppose it can be written f of x equals c0 plus c1 plus, I'm going to write it out a little bit differently. I'm going to have c1 x to the a1 plus dot 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 plus ct x to the at, with the ai's, the exponents, being in increasing order. And I'm going to suppose that the ci's are all non-zero. Okay, so I'm going to have those assumptions, and I'm going to let S be a particular kind of a subset of S. I'm going to let this guy be any closed angular sector emanating from the origin of width theta in the complex numbers. And the width of the angular sector, let's say the width of the angular sector is going to be anywhere between 0 to 2 pi half open interval. So it's a pretty natural thing. I have this sector, it's sitting inside of the complex plane, and what I'm going to be doing is counting roots inside of this sector. Okay, and finally, I'm going to have one more bit of notation. N of S is going to be the number of non-zero roots. I emphasize the non-zero roots of F in the sector S counting multiplicity. Okay, so I have all these different things. So I have a polynomial. I'm assuming that it has exactly t monomial terms. You can call a polynomial like that a univariate t-nomial. And I'm going to count roots inside of an angular sector, and the bound goes like this. The assertion of the theorem is that the difference between the number of roots in the sector and this other quantity, I'll call it theta over 2 pi, times the difference of exponents, the biggest exponent and the smallest exponent, is no bigger than t minus 1. Okay, so this is kind of interesting. So it's telling you that the number of roots is actually close to some kind of a measure. It's some kind of a fraction of something like the degree. And the deviation, the error, is on the order of, it's no worse than t minus 1, number of terms minus 1. So the interesting thing about this theorem is that it includes two theorems at once, and it also has a p-adic, you'll see it has a p-adic flavor to it. So here's what I can say. So first remark is that much more can be said. I'm just trying to keep it simple for now. Much more can be said. You can generalize this in many, many directions, but maybe the most important thing is that you can also, there's also a way to jazz up the theorem. You can also approximate the count. This is for another day. Roots in annuli, approximate the count. And what I mean by that, I mean you have a centered disk about the origin, and you remove a disk on the inside. So you can actually count roots approximately in shapes of this sort as well. So not only can you count roots inside of angular sectors, but you can also count roots inside of here. And you can actually combine the two things. You can actually count roots inside of the intersections of angular sectors with annuli. That's kind of a fancier version of the theorem. And I'll say more about that later. So, okay, I claim that this has a p-adic flavor to it, but let me say what else is important about the theorem. So that's the first remark. The second remark is that the Voorhees-Wilder theorem includes two important results inside of it. So the Voorhees-Wilder theorem definitely includes Descartes' rule, or Descartes' bound, and it also includes the fundamental theorem of algebra. So it's a nice common generalization. Okay, so what do I mean by this? Well, Descartes' bound, this is a result on the number of positive roots for a sparse polynomial. And basically, this is when you take the width of the angular sector and you let it go to 0. Okay, so that t minus 1 is actually an upper bound for the number of positive roots of a sparse polynomial. The fundamental theorem of algebra, what you basically do is you let theta greater 2 pi, and plus you do a little bit more work, So there's a way to get rid of that error. Okay, so if you let your angular sector be of width 2 pi, then you are counting roots inside of the entire complex plane, and not just a fundamental term of algebra. Okay, so now what about the p-adics? I mean, this is supposed to be a conference about p-adics. So let me tell you what's going on. It's kind of a metaphor. And what I mean is that the notion of an angular sector, this is a notion over the complex numbers. It has an analogous notion over the p-adics. And very, very roughly speaking, it's the notion of essentially leading digit. And you're basically going to be looking at roots having lying within a certain radius of a certain leading digit, plus also roots of slightly different norms. So I'll be more precise about this. I'm going to set your theorem for you. And here it is. This is Leinster's theorem. I'll put quotes around it. It's not exactly the way you stated it, but it's roughly in the same direction. So this is a theorem of his from 1997. And the theorem says the following. So suppose P is prime. And same notation as above, except I'm going to change things slightly. So I'm going to have a polynomial. It'll be a Laurent polynomial if I like. And you're going to write it in a certain way. It can be written as usual. F of x equal to a sum of monomial terms plus dot 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 plus ct x to the at, like that. May as well assume that the i's are in increasing order, and I'll assume that the ci's coefficients are non-zero. And now what I'm going to do is the following. I'm going to consider a different kind of a set. I'll let S be the following. This will be the p-adic complex disk of radius. Oh, let's see. I'm going to be funny about this. It's going to be radius 1 over p to the 1 over theta. Okay, sorry, it looks funny, but that's just the way I'm going to do it. Centered at 1, and I'm going to let theta be, I don't know. Let's let theta be a positive rational number, like this. And finally, we're going to let ns be the natural thing. Ns is going to be the number of roots in S. Number of roots. I should say, by definition, these roots are going to be non-zero too. And it's number of roots in S counting multiplicity. Okay. And here's the assertion. The assertion is that the number of roots, not quite a deviation bound, but it's definitely a bound, is going to be of this order. So it's going to be bounded above by a constant times this quantity. So it's t minus 1 times 1 plus, looks a little bit funny. Let's see, I think it'll do, yeah, 1 plus theta times log of, yeah, t minus 1 theta. And I'll put this over log p. And then I'll put that over log p. Okay. So what's going on here? Again, just to repeat, over the complex numbers, what was happening? I had a bound. I had a some kind of deviation bound for the number of roots inside of an angular sector. Over CP, over the p-adic complex numbers, the result is a bit different. Here's the origin. I'm going to look at 1, okay, and I'm going to look at a disk in CP, and I'm going to count roots inside of here. And now, what is the correct analog? Well, the correct analog would be the following. I guess I would also look at a disk centered about P, like this. And I would also look at a disk centered about 1 over P, like this. So that would be the correct analog. So you can sort of imagine that the analog of an angular sector is actually some kind of a union of disks. Okay, that's kind of a very, very rough analogy. And you see that there's this dependence on the number of terms, and it's kind of amazing. Okay, and you could also wonder, well, wait a minute. I mean, the angular sector, if I make the angular sector wide enough, I can get all the complex roots. Is the same thing true for this result? Well, if you look at it correctly, yes. I mean, there's a matter of the relationship between the prime p and the number of terms t, and also the degree, or the difference of exponents. So you can actually make it all work. Okay. Okay. So why am I mentioning all these results? Well, sparsity matters. Okay, sparsity. They're studying the number of terms. Gives you a way to refine. Many quantitative results, many basic quantitative results. And more to the point, there's lots of unsolved problems that are really, really cool, and they're much more interesting and much more challenging if you look at them from the point of view of sparsity. So here's one fundamental problem. So equation solving has been heavily studied over the real numbers and complex numbers, but mainly in terms of degree. A number of variables, and this is natural. Incorporating sparsity gives you more useful results. Okay, so let me give you an important connection. So here's an important thing to bear in mind. Koiran and Saxena and others have proof theorems relating number of roots of sparse or structured polynomials to very interesting complexity questions. So basically questions like P versus NP, and even P versus BPP. So these are big questions coming from complexity theory. I'm not going to dwell too much on the definitions of NP and BPP, but I'm happy to answer questions about these later. So what I want to do is now just give you a concrete result and just show you how challenging some of these issues are. Okay, so that's sort of an overview. I've given you two basic results and one variable, quantitative results. I claim that sparse polynomials are interesting, and they help you better understand how hard it is to solve an equation. And solving equations is something we really want to do in the real world. But before I continue, are there any questions? Si quieres preguntar en español, está bien. Yo hablo español también.
Thank you, Maurice. There are some students in the audience.
Yes.
Who doesn't speak Spanish?
Okay, that's fine.
So, can you briefly tell what is BPP?
Sure. So very quickly, I could just say it this way. These are all decision problems. So these are decision problems solvable. I'll tell you what BPP is in a minute. In time polynomial in the input size. I'll get to BPP in a moment. In the input size. So what does this all mean? Informally, you can define computational problems as anything you can program on a computer. I really mean that, on a laptop. And you can measure time literally by the time your laptop will take to solve a problem. And you start seeing all these different O bounds, order of this and order of that. And so the truth is that, yeah, it'll take a different amount of time if you implement an algorithm on your laptop or my laptop, but in the end, it doesn't matter. Because if you're talking about polynomial time, roughly everything that's polynomial time will still be polynomial time no matter what architecture you use. So if I have an algorithm which takes quadratic time on my laptop, it'll take quadratic time on your laptop, or roughly there, or maybe a little bit off by an order. And so when I say polynomial, I just mean, input size to a power. Okay, it could be to the 100, could be to the 2, could be to the 5. That's all I mean. Now, BPP might be the easiest thing to define, actually. So basically, this one is decision problem solvable in time polynomial, like this. But this is now allowing randomness. So using polynomially many random bits. So now you're allowed to make use of randomization. This actually makes your algorithm more powerful, by the way. Many random bits. Where the answer, oh yeah, and when I say decision problem, I mean a problem with the yes or no answer. Certainly problems can have numerical answers. I don't want to worry about those. That's more complicated. So I'm just caring about yes or no answers. So now here, BPP, different complexity class, this is where the answer is wrong with probability less than a third, less than or equal to a third. That number is kind of immaterial as long as it's at some bound strictly less than a half. Okay, so these are interesting algorithms, and they're more powerful because you're allowing errors in some sense. So the algorithm could end, and it'll give you an answer, but the trouble is you can't trust the answer. You can trust the answer only probabilistically. And you might say this is unsatisfactory, but that's okay. What you can do is run your algorithm 10 times. If you run your algorithm 10 times and take a majority vote, then if there's more yeses, you say the answer is yes. If there's more no's, you say the answer is no. And you can use a little probability theory to prove that then your probability of success is much higher. And so the probability of success goes up exponentially. Okay, and then NP, this is this famous complexity class. This is decision problems where a yes answer admits a certificate of polynomial size checkable in polynomial time. And so the classic example of that, I mean, it's well, here's a simple example. It's actually not the right characterization of NP, but here's an example: factorization. So if you look at an integer and you measure the size of an integer by the number of digits, something on the order of the log of the integer, n, then how do you know if the integer is composite? Well, an easy way to check compositeness is for somebody to give you the factorization, and then you multiply those numbers in the factorization together, and you see that it's equal to n. Okay, so that's a certificate. For compositeness, the certificate would be a complete factorization of the integer that has size no worse than the integer, or a little bit more, and you can check it yourself in time, quadratic, maybe a little faster than the total number of bits in the integer. Okay, so a yes answer is checkable by some simple certificate. I don't care how long it takes to find the certificate, just I assume somebody's going to give you the certificate. Okay, so in any case, these are 3 very famous complexity classes, which we don't know to this day if they're how they compare to each other properly. So the conjecture, this is what people believe. People believe that P is not equal to NP, and a lot of people believe that P is equal to BPP. And I should put question marks here. This is what a lot of people believe, and we still don't have a proof. And these conjectures have been around for decades, and they would really, really revolutionize computation if we could prove these conjectures. Okay, so I've digressed a bit, but now let me say something about solving. Okay, so here is a fundamental question, which has been answered kind of nicely for over certain fields, but not other fields. So a fundamental question. It's also a fundamental theorem. This goes back to work of Smale. And it goes like this: given and random, so random, there you go, polynomial equations, polynomials and variables, I should say, this is over the complex numbers in n variables. Can we approximate 1, 0, one root, one complex root in polynomial time on average? Okay, so this question is really nice because it's very easy to state. At least Smale found a very elegant way to state it, and it's actually been solved. This question has been solved positively in some recent work. So let me point that out. So fundamental theorem over the complex numbers. And this goes to work of Leray, 2017 or so. The answer is yes. And to be more precise, there's a lot of details here. What do I mean by random polynomial? I mean that I pick the coefficients using a particular variation of the complex Gaussian. Okay, I have to use certain kinds of variances. What do I mean by looking for a root? Don't I want to find all the roots? Well, you have to be careful. Polynomial equations can have lots of roots. If the degree is big, then Gauss theorem says that you have exponentially many roots in n. Okay, so that's going to kill you. So what you mean by polynomial time is something kind of tricky. So I could say the theorem roughly this way. It goes like this. For d equal to the maximum degree I of the fi's, so you're working with polynomials, f1 through fn, okay? We need just this many steps on average. D plus n, choose n, and let's see, times this. How many steps am I going to use? I think there's going to be a little more complexity here. Something like this. I forget the exponent exactly. I think maybe I'll take this to the fourth. I think that this is going to be good enough or so. So it's going to be roughly this much arithmetic operations on average. What do I mean by arithmetic operations? Plus, minus, times, divide. I think also the array happens to use square root. Square root can also be approximated, so I'm not going to worry too much about it on average. Okay, so this is what I mean by polynomial time. So why is this polynomial time? Well, here's why it's polynomial time. This comes down to sparsity. This quantity here, this multinomial coefficient, this actually is this guy here. This is equal to the maximal number of terms for one polynomial in n variables of degree d. You can actually prove that. So this looks reasonable. So if you measure the input size as the number of terms, the total number of terms in a polynomial system, if you have n polynomials, n variables, each one having degree d, each one has at most d plus n, choose n, binomial coefficient, many monomial terms, then n times that is going to be the total number of terms. And wow, that's pretty amazing. That's the algorithm takes time about quartic in the number of terms. That's pretty good. It's polynomial size in the polynomial in the input size. Okay, but here's the thing. What about R? What about R? Also for us, what about CP and QP? Okay, so what I do want you to be aware of is that we're kind of far from a solution. This is quite an open problem. So now let me finally mention some positive results in this direction. So The tricky part, what is tricky, is that even counting is hard. Even counting is hard over QP, which is kind of remarkable. So let me give you this theorem. This theorem goes way back. So this goes back to work of, let's see. This is work of Avendano, Ibrahim, Rusek, and myself. And this is from around 2011. And it says that deciding if one polynomial in one variable has a root in QP is NP hard with respect to randomized reductions. Okay, so what do I mean? To put it another way, if you find a polynomial time algorithm, and I should be careful here. This is, I'm using a particular notion of size. So let's be careful. If you measure the size of a polynomial like this, C1 x to the A1 plus CT x to the AT, and this polynomial has integer coefficients, as this, the sum of the log I equals 1 to t of the obvious thing. I'll take AI plus 1, absolute value, multiply that by CI plus 1, absolute value like that. Yeah, if I'll do that, and maybe I'll do this, 1 plus that. There you go. Then, detecting roots in polynomial time, would imply a collapse that people don't believe. It would imply something like, BPP. Oh, let's be careful about this. No. Something a little bit better than that. ZVP equals NP. And the point is something doubted. This is something close to P equals NP, which is doubted. Okay, so what I'm saying is that you can relate the complexity of counting one polynomial, the p-adic rational roots of one polynomial, one variable, sparse, to complexity theory in this way. It would be nice if you could prove definitively, okay, I can prove that there's no polynomial time algorithm. That doesn't seem to be possible yet. What you can do is show that this problem is related to a famous problem for complexity theory. And so then if you did find a polynomial time algorithm, you would prove that P equals NP or something close to it. And also if you prove that there's no polynomial time algorithm, you got to prove that P is not equal to NP. Okay, so in other words, this problem is closely related to complexity theory in some way. So, okay, counting is hard. Yes, yes.
I want to make a comment. I think that this result implies almost immediately that the Bursa local zeta function attached to one polynomial in one variable is also in the class NP hard with respect to randomized reductions. And then from that, you get that the computation of a congruences modulo P to the n is also in that class.
Yes, there's probably going to be lots of reductions in between these different problems. So you have to be a little bit careful with these reductions because sometimes you can go in a different route and prove it more directly. Okay, so yeah, I mean this is a very basic problem, and thank you. I hadn't thought about that. So there's been recent work on computing equals to zeta functions, and there's some positive results, but then this is probably going to imply a negative result too. So I should add, there's results that are positive for computing Igusa zeta functions. There's work by Saxena and others, and also one of my students.
But all these results, the positive results, okay,
yeah, they're in terms of degree. They're in terms of degree, not in terms of sparsity. So this is the tricky thing. What's subtle here is the notion of size. Okay, so this is a theorem which is set in the which is in the setting of sparsity. So if I want to take into account measuring size this way, then things become more challenging. Okay, but if I don't care about sparsity, if I just care about degree, then it's easier to get algorithms that are polynomial in the degree. Okay, but also I claim that you're missing something. So if you look at a polynomial of degree 1,000 and it has 1,000 terms, okay, that's one kind of polynomial. But if you look at a polynomial of degree 1,000 and it has 3 terms, that's a different kind of animal. Okay, so theoretically, maybe you should be able to do things better if your polynomial has degree 1,000 and it only has 3 terms. Okay, so now let me mention something positive in that direction. Okay, so while this result is negative, there's ways to get around it. Perhaps averaging helps. Okay, so that's a standard thing. Whenever you have a problem which looks hard, maybe it's not that the problem is hard, it's more that there's just a few instances that are really bad. And maybe also it's hard to identify which of these instances are bad. So then what if you average? And if you average, then maybe the problem is actually efficiently solvable on average. This is kind of what happened with Smail's 17th problem. Sorry, I should go back. This is known as Smail's 17th. This general problem about solving systems. Okay. Okay. Beethoven's 5th, Smail's 17th. Okay, so also, what about small examples? That's another question. Small examples. So this is where it gets interesting. So what happens if you do, say, one polynomial, one variable, 2 terms? Okay, so here's a theorem. And so this one, I'll say this one is anonymous, but I also made a refinement of it with a student of mine. So this is, yeah, this is pretty recent. This just appeared in JNT. This is not the main theorem, but this is just sort of a warm-up. You can, let's see. I don't even want to take credit for this. This is just older. I'll take credit for something harder. You can count the roots in QP of any binomial, C1 plus C2, x to the d, in time. Oh, I forget the exact bound, but it'll be something like, log of p. You can take this to the 2 plus little o of 1. Okay, so this is not, if you know your number theory well, you can figure this out. I mean, there's sort of classical results about, how you detect d roots over a finite field. There's also classical roots about detecting d roots over QP. And if you put it all together, it's not so bad. So this is polynomial time. So this is kind of the opposite end. I mean, I just told you that deciding the existence of roots is NP hard. I did. But that's for arbitrary polynomials. Now what I'm doing is restricting even further. I'm just restricting to 1 polynomial, 2 variables, let it be high degree. And one more thing, sorry, something I'm forgetting here. Yeah, I should have said log dp. It depends on the degree as well. There you go. There you go. So it depends on the degree as well. So logarithmic in the degree, logarithmic in the prime p. Okay. Now, here's where it gets more interesting. So this is where I come in, plus one of my students. And you can do it this fast. Yes. You can count. Be careful with this. Yeah, this is where it gets subtle. So I take it a little bit farther. So for 3 terms, you can do the following. In deterministic time, order of p cubed. There we go. There we go. Cubed log p, sorry, log of dh. Take this guy to the 4 plus the log of 1, and multiply this by log cube d. You can approximate all the roots of this polynomial f of x equal to c1 plus c2 x to the a2 plus c3 x to the a3. Let's say 0 is less than a2, less than a3. And this I'm going to call d. And I'll also say that the absolute values of the ci's are bounded above by h, which is a positive integer. Let's see, in QP. Okay, so let's concentrate on this result for a minute. I'm going farther. So I'm going to 3 terms. And not only am I going to count the roots, I'm also going to solve for the roots. What I mean by solving, I mean I'm going to give you approximations for the roots. Okay, so when I say approximations, what do I mean by that? So the approximations are going to have a certain size. These are going to be ratios of rationals, sorry, of integers. And let's say these are integers of height. You know, take log of the integer if you like. Not so bad. P times log squared dh times log d. Okay. So, okay, like I said, detecting roots over the p-adics is really hard in general. So what happens if you restrict really, really tightly? So you look only at like 2 terms. Well, things are easy. Solving is not so easy though. I'll say more about that. What about 3 terms? Well, counting and solving aren't so easy, but you can do something. And now here comes the interesting part. The interesting part is the dependence on p. So why do I have this really bad dependence on p? Okay, so that's pretty serious. And I claimed that maybe you can do something about it, but it comes down to an even more basic problem. Okay, the dependence on p. So here's the problem. The problem is that I don't know how to get rid of that dependence or how to improve it, and it's related to something more fundamental. So here's the issue. A simpler problem, believe it or not, is computing, I could say a subproblem, is computing d roots over a finite field in FP. And here's the thing. We still don't know how to do it. We still do not know how to do this. How to do this in time, log of p d to the O of 1. This is the truth. So even this fundamental problem, you want to try to solve polynomials with 2 terms over the p-adics. All right. A subproblem of that, if you're just going to approximate the roots within distance, p-adic distance 1 or 1 over p, is to solve over a finite field. And taking these roots over a finite field, we barely know how to do that for the case d equals 2. Okay, so in basic number theory, you study how to compute square roots over a finite field. And there are these classical algorithms, Tonelli-Shanks, and these other algorithms, which are randomized and go fast. But as soon as you go to a higher degree, the complexity gets much more complicated. We don't know how to solve just the D3 problem in this time. That's an open question. And so you see the dependence on P in this result involving 3 terms. That's where this is coming from. I mean, there's a dependence on P, which you can try to reduce in some cases, but you start bumping into really difficult problems. Another issue is the amount of accuracy you need. That's something else which is going on. So another issue, I'll say here, is accuracy. And the issue is, how much accuracy do you need to approximate roots? Well enough for Newton's method, or Newton-Hensel iteration, to converge quickly. Okay, and this is where it gets a little bit weird. So in the case of binomials, it's actually easy. In the case of trinomials, it's a little bit harder. And in the case of t-nomials, just 4 nomials already, it gets harder. So here's how much accuracy you need. For here, the accuracy is very, very small. I'm trying to remember how much accuracy it is. It's basically constant. I mean, it's basically something like 1 over p squared is good enough, something of that nature. For trinomials, the distance bound is something like a little bit more difficult. It's something like distance is 1 over p to something, and this is going to be p to something on the order of like p cubed log dh cubed. So that nature. And for 4 nomials, it gets worse. So for 4 nomials, you need distance of 1 over p, but now it's something on the order of exponential. So it's something like it's going to be exponential in log dh. It's just worse. It'll be something like let's see. Gotta be careful here. Yeah, it's something like dh, I think, to the square, or something of that nature. So the point is that if you want to solve over QP, this is your last hope. And then as soon as you go to 4 terms already, things get worse. Okay, so you really, really need averaging. So I haven't really spoken very much about averaging, or how you're going to do things over randomized inputs, but that is definitely the next step, is to analyze more closely what it means to talk about randomized inputs and to do things fast on average. Okay, so this is as much as I want to say for now. This is I've already spoken for about 45 minutes, and I know you need time for questions, and I know you want to stick on your schedule, so I'll stop here. Okay, that's as much as I want to say for the moment.
Thank you.
Okay, thank you.
Are there comments or questions? I have a question, Maurice. Could you please comment about the complexity of factoring polynomials in one variable over the p-adics?
Yeah, so that's an interesting one.
Sorry, I'm thinking in terms of if this problem is harder than the problem that you are presenting here, or is weaker, I mean, simpler.
No. It's a more complicated problem, because what I'm basically doing, I'm basically telling you how to fish out the linear factors, and so that's where it gets complicated. So the question was this: what is the complexity? What is the complexity of factoring over the p-adics? Of factoring in QPX. And so what I've done essentially, so I essentially studied how to get the linear factors, how to approximate linear factors. And of course, you have quadratic factors and other factors. I haven't really entered into that. But there's, of course, classical work, and then there's more recent work. I mean, there's this work of Montes and others. Part of the problem with the p-adics is that when you want to factor over the p-adics, you don't have really finite answers. You can actually have answers that involve sort of p-adic numbers, which go on forever. And so the true answer is more of an approximation. And so you can still discretize. You can still say, okay, I can't really ask for the full answer. So let me ask things related to the answer. So I want to ask how many factors are there and things like that. So those questions you can answer. And they take a bit of work, but you can actually answer them. And then the trouble is that the discriminant pops up. And so that's sort of one basic quantity which gets in the way. So the discriminant or its valuation is hard to escape. And for trinomials, I'll just make this comment. For trinomials, the discriminant is actually kind of nice. Discriminants are nicer. Discriminants are easier to handle. Another comment too, here's another little note which is interesting to observe. On average, discriminants are well behaved, whatever that means, over the complex numbers. Is this true over CP? This I don't know. This is an interesting question. I think it should also be true, but I think it requires slightly different techniques. So this is something that people have made a lot of use of in recent years. And remember, the discriminant. Yeah, you're welcome. Yeah, but just remember, the discriminant is a measure of how far apart the roots are, and it's kind of natural to expect. Like, yeah, of course there exist polynomials where the roots are really close together, but on average, polynomials shouldn't have the roots so close together. That's the hope. Okay. But thank you for asking.
Thank you. Are there more questions or comments for the speaker?
There is one question.
There's a question in the chat.
Yeah, let me check the chat. Let's see, is there a paper where one can find the results? I mentioned the first part. Yes. Oh, yeah, sure. So Jose HDZ. Okay. Yeah, I can give you some references. So let me see. Maybe I can type in some of the references. That might be faster. But there's been quite a bit of work. I'd say Avendano and Crick wrote a really nice paper. So Avendano and Crick around 2000 and something. I forget exactly, 2000 and something. And I can't remember. I think it was Journal of Number Theory. Yes, have a very nice paper. Lester's work. So, okay, it's in the chat. I mentioned Avendano and Crick. I think it's Journal of Number Theory. I forget exactly when. I want to say 2011, but I'm not sure about the year exactly. But if you just Google it, you'll find it. And so that definitely covers some of the work. I should also mention, you should read both papers. So let me say this, that Lenstra wrote 2 papers on finding p-adic factors around 1987. Yeah. In a proceedings book in honor of Andre Schinzel. There you go. So I highly recommend you look at the 2 original Lenstra papers, mainly because Lenstra is a master. Right? Lenstra writes really well, and he writes about important things. And Avendano Crick's papers is also really wonderful. But I do want to point out the techniques are rather different. So I would say that Lenstra's techniques are very interesting and also very fundamental. Avendano and Crick improve Lenstra's work, and they do some very interesting tricks. But I think it's important to also remember what Lenstra did in the beginning too, because he makes a lot of important insights that remain important. So whatever improvements you make afterwards. Thanks for asking.
Okay. Thank you, Maurice. Let's thank the speaker.
Thank you. So I hope you have a good conference. I'm sorry I'm not there. I wish I could be there. It's been a long time since I've been to Mexico, and it's a very beautiful place.
Bye-bye.
Bye-bye, I'll see you.
We have 5 minutes before the next talk.
Okay, good.
Si baja de 32 de abril. Si baja de 32 grados.
Ok. No, yo creo que así está bien. No, yo creo que así está bien. Señales. ¿Sin micrófono? Sí.
El micrófono lo necesita Brian, porque acuérdese que.
Para los que están.
Para los que están, no, no es los de la sala, los que están en internet.
Sí.
Si no se lo pone acá.
Hola, hola. No, hola. 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 Hola, hola. Sí. Sí. Salir corriendo. Ok, aunque no hablo muy fuerte, entonces no creo que haya hasta rebotando. No, no, esas solo son mis notas, el cosito está por ahí. Minutos terminamos. siempre me mata es la introducción. Lo que siempre me mata es la introducción.
Okay, guys, it's time for the next talk. Okay, it is a pleasure to introduce the next speaker, Mr. Brian Andres Zambrano Luna. He is a PhD student at the Cimpa staff, the Center for Research and Advanced Studies of the National Polytechnic Institute. That's difficult. So Brian is going to talk about networks and PDEs on the p-adic frame. Welcome, Brian.
Thank you so much. Can you hear me? Well, I can. I came out in front of you, so doesn't count. Right now? Good? No? I think it's working. Okay. Good afternoon, everyone. As the professor said, R is called networks partial differential equation on p-adic frame. The idea of the car. Hi. Okay. As I said, the idea of the talk is present a work we did with the Professor Wilson, the interaction between networks and p-adic analysis. Okay. In this work, we introduce a generalization of networks. We call p-adic cellular neural networks. We was, it said, mathematical generalization. The cellular neural networks were presented or introduced by Chua Yang in the late 1980s, more or less, as a network in the purpose of process images. Since the distribution of that network, the cellular neural networks, has been studied intensively in different fields and different applications, and well, that is the reason we started. The network that we introduced essentially are divided into two kinds. The first one, the PI discrete cellular neural networks, CNN. In that kind, we have finite cells, and they are organized in a hierarchical way, and they are modeled by a system of ordinary differential equations. The second one are the p-adic continuous CNN, and well, in that case, we have simply many cells, and again, are organized in a hierarchical way. In this case, they are modeled in a with only one integral differential equation. Okay, and yeah. Different, in addition that the theory we study in neural networks, we propose a way to visualize the behavior of that networks, essentially in two ways. One using Cimpa, another using embedding from PP to C, and plot that the networks over that. Yes. All the results I will present are in this reference data. Okay. The scheme of the talk is the following. I will recall very quickly some notion of p-adic number. This something they will study over this course. I will introduce three spaces that are the base where we define the networks. And later I will introduce the definition of the discrete and continuous cellular networks. Okay. Here also I will present the result of the chain, and I don't present the detail, but I try to explain what it means the result. And at the end, I will present essentially two simulations. One is where we use the key map and the fractal map. Another is something like application of these networks in the edge detection of images. Okay. Let's start. As usual, the p-adic numbers are, the comparison of Q with respect to the p-adic norm. The important here is that remember that the p-adic numbers have a unique representation of the series this form. This is important. Well, some facts about the topology. QP is a total systematic space. That means that the only subsets of QP that are connected are the point sets and empty sets. Clear. The words are compact sets. That implies well, that implies we have the armature. We know that QP is a group. This is important, and it's important because with the armature we do all the analysis we apply here. And here we have that the words are similar sets. That means that essentially they are fractals, and this is very important when you try to find applications of QP in other fields, particularly in biology, something like that. Okay. At the end, we use fractal. And this article is also, I don't know how to use the name, introduce an embedding from QP. Here, CP simplicity, but the embedding is for QP to C. That depends on two parameters. And we have some nice representation of QP. For example, for P equals 2 and this parameter, we have these plots. And you can see when we change the parameters, S, I can say S is a complex number with norm less than 1, and M is a natural number. But you can see that when you change a little bit the parameter, we have different representation of CP of this case C2 and this case C3. Yeah, it's interesting. I will be back here later. Okay, something about the test function. I want to remember the test functions are functions for QP to R. In this case, we are take R as a codomain. They are the functions that are locally constant with compatible. Yeah. It's easy to prove that this is the same as the linear combination of characteristic function with real, yeah. Okay, we don't know the test function. Okay, that was all the definition of the we use in this, understand this talk. Okay, let's start with the definition of some spaces. The first space is X sub infinite, or sometimes called C sub 0. Essentially, the completion of the test function with respect to the supreme norm. And you can prove, it's so difficult, that this is the same of the test of set of functions from QP to R that are continuous and vanish at infinity. Over this space, we will define the continuous PIXCNN, and that's the reason we introduced that space. The second set space, in this case, is a group, a quotient group, can be thought that the PIX numbers that have this representation, simplicity. Yeah. Why we introduce this space? Because as I did said in the introduction, our network has a hierarchical structure. Yeah. To give that structure to the networks, we will identify the cell with the elements of this group, and this as a natural structure as a thing. That's the reason we introduce them. The second space, the third space we introduce, we define is this. This space is the superb vector space of the test function, defined by the characteristic function of both with center I for Si in this group, and radius Pn to -7. Okay. Why we introduce this space? We have essentially the same. Because we want to use this from evolution equation, and we need to work on Banach space. That is the reason we introduce this. Of course, this is a Banach space, and essentially that is the reason. Okay. Now I will show you the definitions. First, the classical definition of cellular neural networks that you and Jan presented in the first article, and the generalization in the definition we propose. Yeah. Okay. The first is the original definition, the definition that Chua Yang proposed in his article, their article here. essentially it's a dynamic system of the cells, with a set of cells, which is modeled by this system of differential equation. It's a little bit difficult to understand the first, but let me explain the meaning of this term here. This term here is the feedback of the network. Y is the output of the network that depends on a non-linearity function. Usually they propose this for application. The second term here is a feed-forward cell, and U is a external input of the network. It has a lot of parameters, and C is a thread. It's natural when you work in a network. Okay. Usually the image that you have to take when you work in this network is this. It's essentially lattice where the squares are the networks at the cell, sorry, and the edge is the interaction between two different cells. Yeah, this is the usual geometric origin of this network. Okay. It's natural. All these are the work to change the geometry of the network in a hierarchical way. Yep. Where we transform or we change the geometry of this definition by variatory structure. Okay. That allows us to define this definition. This is a discrete, the PI discrete CNN is the same as before. It's a dynamical system over a set of cells that we identify with the elements of this group. Yeah, that is the with that identification we change the geometry of the network. As you can see, essentially it's the same. We have the same meaning of the system differential equation. We have one ordinary equation for each cell. Okay, it's important to mention here that by intuition is not directly, but you can take the four networks as a particular case of here. Where how do you do that? You only have to make identification of matrix with the response because they are two finite space. Okay. But when we change the geometry of the network, we have more exotic structure of the network. For example, we will take this subset of cells and take all these parameters. Our parameters equal 0 is like this. We have this geometry of the networks. We can see that it's really different as before. But they are interesting because you can see that two cells are connected if only if they have a common ancestor at level 1. Yeah, you can see here how the tree structure of the network, affect the connection between the cells. Okay, but yeah, there is the filter. Okay, now when we doing this article, we were more motivated to work in a network that have a lot of cells, a lot of function cells. That is natural. It's a natural question, and when we do that, this that question or that situation get to this definition. It's a continuous cellular network. Essentially, what we do is identify its element of QP with a cell and taking the definition before in a continuous way. Yeah, this would say translate into an integral differential equation with the same meaning. You can see it's essentially the same. How we work in an integral, and well, y a, b, etc. have the same meaning as the Theorem definition. Okay. Well, until this point, well, we probably asking what is the connection between this definition and the before? Yeah. So one is discrete, the other is continuous. Well, the answer or the intuition we have about this is the following. When you are trying to study networks, we have a lot of cells. It's difficult to study that network, difficult to understand the behavior of that network. Then it's natural to consider that network we have a lot of cells as a continuous. When you translate that discrete networks in a continuous networks, we have something like this. And in this case, you can apply theory of partial differential equation on Banach space. In particular, we use evolution equations. And that is the one technique that you use to understand the behavior of a discrete network has a lot of steps. But on the other hand, when you have a continuous networks, after you study more or less you understand all is the networks, you would like to visualize the network as pulses in your case. For that, you need to use a discrete network that is approximation, a very well approximation of the continuous version. Yeah, there is an interaction between the two definitions, the discrete and the continuous networks. Okay.
Is there a bit one X, A, B, Y, U, and 0%?
Yes, yeah. The A is the feedback kernel, is a feedback. Yeah, of the network because Y depends on the output of the network. Yeah, depends on the state of the network. Yeah, X is the state of the network. The third X, capital X is the network. The other X is the state of the network at time is the time. This is clear. And where B is the feed forward of the network. This is some application is important. We'll see that later. And U is the external input, and X is abstract. Something that you need to put when you're looking for certain information in the network. Yeah. And well, you have some hypotheses, natural. Okay. Well, great. This is the definitions. The natural is to start to study this object. Okay, this is the main object we want to study. Yeah. Okay, let's start with the first theorem. It's something like existence theorem. It says when you have the kernels are L1 function and the other parameters are in this order space, then for any initial condition and any time, there exists a continuous function here from 0 to time, the space we are working on that satisfies this identity. Yeah, this identity. The function that satisfies this identity are called Malik solution, and they are the first solution you look for when you are working in evolution equations. Yeah, it's a normal solution that we do. But in our case, we can prove that that function, that is unique, is differential function, is a differentiable function, and of course satisfies the dynamic of the network. What it says, when you have you establish a dynamic with this condition, then there exists a network that satisfies that dynamic. Yeah, this is the meaning of this theorem. Okay, the next is an important. I believe it's very important in case of application because it says when you encapsulate the information, the parameters of the network, what I mean. The support of the kernels are in a board radius PM example, and the other parameters you see and the initial condition also have support contained in a board PM. Then the solution, the network that satisfies that dynamics that we know exists, also we can encapsulate in that board. Yeah, what it means if you encapsulate the information, all the dynamics is inside that board. Energy don't escape that. Yeah. Okay. And the last theorem I will present here. There are other result we have in the problem. This is the principal, I believe. The other theorem is a bounded theorem. It says if X is the It's a network that satisfies some relations of dynamics. Then there exists a constant that doesn't depend on the space of time, only depends on the parameters of the network and the state of the network. But it means that in any time or in any time and any space, the network will act. Always will be a dynamics that you probably can follow. Okay, this is important. And as a consequence of this bonding, we could give necessary condition for the existence of stationary solutions. What is the condition? We define x sub minus as the infimum limit and x sub max, x sub plus the supreme limit. Then if these two functions are equals, then that function is a stationary solution. Yeah, this isn't the existence of a stationary solution in this case, but we did have necessary condition. But also, we could give a condition here, 6, that ensure that the stationary solution is different from 0. That is what means that when this is bigger than 0, the dynamics will be working on numbers. Okay? Question? Okay. Now, okay. Now, I want to show you that the intuition that we have in the connection between discrete networks is correct, essentially, mathematically speaking. For that, we need to introduce two functions, Pn and Em. Pn is essentially a projection from x sub infinity to x sub m. Why we introduce this function? Because by definition, the two networks live in different spaces. We need a function that connects data spaces. That is the reason we introduce that. Okay, they are with now functions. Okay, what the experiment says? Yeah. Okay. Let x be a solution of a continuous cellular network with an initial condition x0, x0, and let xm the solution of this Cauchy problem. At the first time, you can see what happens with this Cauchy problem. But when you expand this this part of here, you use the definition. I use that is the previous part, is the nonlinearity of the integral differential equation. This is in other words, is a compact form to write a discrete like CNN. Yeah, essentially this is a discrete CNN. Then when m goes to infinite, then the discrete CNN approximate very well the continuous CNN in the supreme number. This is important because that's important aspect. Really well. This is the fundamental theorem to apply the serialization of the simulation. I think this is the simulation that I will present there. Okay, let's start. This is a atomic simulation, you say, but it's important to use some comments. In this case, we take p equal to n equal to a. We have these kind of points. We can this we do these kernels essentially are exponential. Okay, and we are I'm working in CP or simplicity. Yeah, the theorem 2 says that we encapsulate all the dynamics, all the parameters, the dynamics is in that work. We can work in CP. Now we use this input, this curious input is something like similar function, and we use this threshold. With that threshold illustration, we visualize the behavior. No, nothing more special than that. And we use this nonlinearity because the classical one. Okay, in this case, this is the input as a key map. The color represents the energy, or the levels of the energy of the input. Here, input, and here is the heat map of the network for all the points. Yeah. This is important in the part because they present in detail the behavior of the network point by point. Yes, you can see, well, a little bit, you can see the behavior of the point of the network, next state of the network. Well, that's the first thing. And the second is when you try to understand the dynamics of the network in a global way, the better I think you can do is plot the network in a fractal using the environment that I presented before, where I told you outside the details for the environment. Okay, this is the input here over the fractal in C3. Yeah. And here we can see the dynamics of the network over the fractal. Yeah, this is the initial state, is 0, but we are introducing an external input. We can see the dynamics changing over the time. You can see the different. This plot have different information that in the case of the heat map. The two are, I believe, very okay. This is interesting because you can apply the simulation in different contexts, different differential equations. Oh, yeah, integral differential equation. Okay, that is the first simulation I would like to present you. Now this is the last thing we did. This is an application. We don't think this is an application. Was this periodic CNN in mesh processing? I will do some talks of what we did this. The first, all the mesh has this size only for simplicity. You can work in a bigger size, take more time. The second, we will take black as -1 and white as 1. Yeah, it's because you can see the activation function that when you plot that, it's natural to consider that identification. Okay, since we have to apply a simulation and my laptop doesn't support work over all the mesh, I need to divide the mesh into sub-mesh of this size. Essentially, night peaks as high and night peaks as wide. Yeah. Later, for a sub-mesh, we transform the image into a test function. That is a curious part. Can explain later here. And with that test function, we process with the periodic CNN. Sorry. A periodic CNN, I will later show you what is the dynamics. And after that, with the result of the output of the CNN, that is a test function, the Theorem 2 ensures that that is a test function. It's important of the Theorem 2 that I presented. We transform that test function into an image, and later we merge all the images to only one. Okay? The example of the dynamics we take are this: P is equal to 3, M is equal to 4, so we have 91 points, 91 pixels. A is this test function, and B is defined as this. The first thing you can see is this is a continuous function, but this is a Ergodicity function. Yeah, this is still the theory. The mesh are taking as input of the mesh of the network. This as a threshold we took by hand was the best option, and X0 for all the mesh for all the examples I have are with 0, and this is the expectation. Well, you can ask me why I put or why we took this type of experiments. Well, they were motivated by one that Chua and this this organization proposing this book isn't the same, but is motivated by one they proposed. And something important to hear is that the images are taken from the dataset of this package from Python, ski image, the name. Well, I took that. I used that package to to resize the image, etc. Okay, the first is a simpler image, it's a binary image, so only take -1 and 1 next pixel. And well, when we use the network with the initial state is 0 by definition, but later you can see how the networks try to learn the partner of the image and later try to, as we say, do or find the edges of the image. Yeah. Here is the image, here are the edge. The white points are the edge and the other points are not. Okay. This is a simple image, but we have others a little bit more difficult. For example, this is a classical image that you use when you try to process image different techniques, the cameraman. And here we can see that works pretty well too. Well, you can see is the find the edges at the result time. You can see that I only put time equal to 6. Something important. Well, I will explain that later. After this time, the image is the same, but the reason I don't put more. The simulation I did for more than time equals to 15. And this is the most difficult image I processed here. And well, it works more or less quite well here too. Some comments, the numerical implementation they use was the Euler, because we are working in a semi-group generator, continuous semi-group, and the step of the difference, the method was here, 0.05. Yeah, is the step.
Does that then have a unit? Does that then have a unit? It's like seconds or something.
And then, well, yeah, I don't know why I hear that type.
No, he's asking about units. 3 seconds, 3 hours, or just
iteration. Just the iteration. Yeah, because you take a time and 0, 10 and divide by interval in pieces of 0.05.
Gotcha.
Yeah, this isn't the time of the this is the for this image in a quantity time, you say it's around 1 minute or 15. There is a 15 by 0. This is number steps. Gotcha. Okay. And well, thank you so much. Let me do some sorry. Comments about the reference, because I believe it is important. The first in here, this reference is the when you find the embedding I present to the fractal forms of CP. Here is the book that find the motivation of the network, the original article. Here is the reference of the library I use for the implementation of the Python of the networks. And this is the program you can see all the details and more information on how we process and implementing the networks. Okay, that's it.
Thank you. Are there comments or questions? Okay.
No, go ahead.
Thank you. I have a general question. So, do you know some application of the p-adic number in relation with the segmentation of pictures?
No. Is the before the application we find that numbers and image process.
Please, you can the first reference. Please, I can
see the reference.
Okay. This
or the third one.
Yeah. Okay. Okay.
So my question is about P. I'm curious about P. You use P equal 3 in all the cases, but how does it change if you use another P? How does it impact in the network that you're using, etc.?
Yeah, this is a good question. Even I don't know what is the answer. The reason, okay, so I say it again. That is a good question. Even I don't know how to choose the P because it's difficult. The reason why you use PT13 because when you study the classical mesh analysis, mesh processing, they use the network. The neighborhood is 3 times 3. For this, so the reason I use P equal 3. But until this point, I don't know how to choose P or how the P affects the process of the mesh. Also, there are some questions because the way we divided the mesh is 3 times 2. We can ask what happens when you take more swing mesh bigger, but it has a problem because when you take bigger swing mesh, the time of processing is more slow, but you have more details. So you have to play a game with that case.
Are there more questions or comments? Oh.
One question is about you constructed p-adic cellular neural networks, but they were also real cellular neural networks. Right? This is based on the work on real values cellular neural networks.
Yeah.
Okay. So, what are the differences? Is there an advantage over the p-adics and the computation maybe, or something like that?
We don't.
You have not.
Well, the advantage, I could say that when you try to discretize a continuous version, it's a natural way. No, the theorem says that you can't discretize that in a natural way. Because in a real case, you always assume that the discretization is a lattice because you need to transform integral. You use the Riemann interpretation of the integral. That is the reason you use that discretization. The question is why we need to use a lattice to represent that discretization. Well, we can use a trick. That is, I don't know, motivation. But I don't know. We're still working in that.
Are there more comments or questions? Okay, let me make a quick comment about this work. The motivation behind the continuous models is the following. There is right now a need for understanding hierarchical networks. Hierarchical networks means networks where the neurons are organized in tree-like structures. In typical applications, there are millions of networks. So an important problem is to understand the dynamics of these systems. A natural approximation consists in finding continuous models. Okay, so really the motivation behind this p-adic continuous models is to understand very large very large hierarchical CNNs. Okay, one interesting thing about this result, I mean, the last simulation is that these networks can process real images. Okay, okay. I don't have more comments, so let's sign the speaker again. Now we have a break.
Yes.
Okay, we have a break, and then we come back at exercises. Let me tell you something. During this time, I mean, if you have comments, questions, if you want to do some problems, we can do that. But also, we want to present the graduate program that CIMAT offers. Maybe some of you are interested in this program. And also, we want to present the graphic program with UTRGB. We're gonna use just 10, 20 minutes for this activity, okay? So see you at 5:30? No. At 5. No. Okay, let me see. I have no.
It's the exercise session, so if you want to.
But we have a break right now. Yes, we have a break. And after the break, we have the exercise session. And in the exercise session, as a part of the exercise session, we're going to have these two short presentation of these guided programs. Okay?
We have a 10-minute break, yeah. It's live, and we have the next exercise session on 9:30. This is not 20 minutes.
Maybe we have another break or. You want some? Sí, agárralo, que no sé. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Grabamos esto, ¿no?
You are supposed to speak English.
Okay, so.
Okay. No.
Okay, the slides and the Spanish.
The slides and Spanish.
Well, no problem. No problem.
Okay. Check.
Yeah, because
Cambiar el.
1, 2, 3. Creo que son 3.
Okay, but I think they are not interested. They are ready for some fisheries in other places.
Okay, so we're gonna have a couple of brief presentations about the study programs of the institutions that are supporting the 2 educational institutions that are supporting the conference. So first we have Luis Delante, who is director of graduate students here in Cimpa. And then later we will have another presentation about the University of Texas.
Okay. Well, thank you very much, especially to the organizer for giving me the opportunity to talk to all of you. The slides are in Spanish, but I think it's not so important. You can understand what's written there. So I'm going to explain a little bit how the program of basic math works here in math. I guess everybody's on the math is right. Are there comments on the road? No, there are no comments. So, well, the department is divided in several areas: functional analysis, algebra, regular geometry, differential geometry, applied math, dynamical systems, topology, and combinatorial geometry. But this written there is a number of researchers in every area, and so this means that we have 9 researchers working in functional analysis, and this number means we have 6 permanent positions working researchers with a permanent position working on algebraic geometry and algebra, 3 people which belongs to something that is called a cátedra CONACYT. That means they work not directly for CIMAT or for CONACYT, which is the National Science Foundation of Mexico, but they are appointed to CIMAT. Okay? They got the payment from CONACYT, they are appointed to CIMAT. And then we have 2 postdocs. And this means we have 8 people which are permanent and 1 which is this CONACYT cátedra. These are permanent people. And here we have 4 people which are permanent, 1 which is a joint professor. That means he works originally at UNAM and comes for 1 week every month. But he is one of the leading professors in knot theory, so it's important for us to have him here, even if it's only 1 week a month.
There are 2 people from CONACYT Cátedras and 1 postdoc. And this is something which is interesting for the Mexicans, because they know what this SNI means. It means that we belong to some research system, national research system. So this is the people from the researchers that belong to the system. Okay. So some of our professors have been invited to give particularly important lectures, like this one. This was a lecture on the International Congress of Mathematicians in India in 2010, long ago. But it was by invitation. It was not something he asked for, but the other way around. They invited him to give a lecture there. So it's really an honor to be able to give such a lecture. Of course, we would like to say everybody has been invited. It's not the case. At least one of us has been invited. There are several international thematic semesters running around the world. This is one who took place in the Isaac Newton Institute, and some of the people working in the area were invited to participate in this thematic semester. So it was also a recognition to the work done by the people here. Now, something that we really enjoy telling is that some of our students, while they are still doing their studies, their graduate studies, are able to publish their work. So there are several international magazines, international publications, at least 6 students doing their PhD, were able to publish their work before they got promoted, and 2 of them were in some memoirs of a Congress, an international Congress. This is one of the articles. It was published in Acta Arithmetica. Mario Goicoechea later went to Switzerland, and he enjoyed being there. And this is one on abstract analysis, P and P convexity of Banach spaces. Omar is, by the way, now a researcher at Merida, Simat Merida. And now let me tell you a little bit. I don't really tell you anything about the program. I'm just telling you about the convenience of it. Right?
That's a good strategy.
Right. So the PhD program is essentially free. You have to take 2 courses. The courses are decided by yourself and the advisors. They tell you, okay, you need to learn a little bit more about homotopy theory, you have to take the course, or something like that. And the rest of the work is your research seminar with the advisor does it. The program is planned to be 4 years, and we are lucky to be being able to advertise some scholarships, which are not our own scholarships, are given by the Mexican Science Foundation, which is called CONACYT. Almost all our students get this scholarship, so something we can advertise as well. But the most interesting is what you can get from coming here. Besides your courses and working with your advisor, you can participate in a school like this. There are a lot of schools going on all the year. Last year there was a Cimpa school on periodic Hodge theory. This year is this school. 2 years ago there was a school on algebra, Cimpa school on algebra, and so on and so forth. So there are a lot of schools, and there are some research projects which are interesting and where you can get involved into. So this is one of those